Namaskar, Adab, Shreshth, 𝐂𝐤𝐴𝐻, hello and welcome in GATE Wallah. So student, this is one short series, and as you all of you know, in one short series, in each lecture we complete one entire chapter or one entire topic of any subject. Like I am dealing machine side design subject with you, and in the first lecture of one short series I have already covered brake chapter completely. In second lecture I have completed clutches. In third lecture I have completed design against static load chapter completely. After that, in fourth lecture, I have completed design against fluctuating load chapter completely. And today is the fifth lecture of this one short series for machines design subject. And today we will complete welded joints chapter completely. Means the topic or chapter which we are going to discuss today is welded joint. So we are starting. Before starting, it is brief introduction about me. As you all of you know, my name is Ramanand Bansal, yours RB sir. I have cracked GATE in 2014 with All India rank 70 in mechanical branch. Then I got selected in IOCL, HPCL and BARC. Finally, I have joined IOCL as operation officer in Hazira Terminal, Surat. After working in IOCL for 1 year, I left the job to pursue my passion towards teaching, and since then I am teaching in the GATE in the field of GATE and ESE. So it is brief introduction about me. So today the topic or chapter which we will discuss is welded joint. And for today's lecture, this will be our lectures flow. In welded joint chapter, first topic which we will discuss is introduction of welded joint. Okay, what is welded joint? In brief manner we will see. But here we will not study what is welded joint in detail, how we do welding, what is gas welding, what is flap welding, what is arc welding. These things you will cover in production in topic, manufacturing engineering topic. Here we will discuss welded joint with respect to design point of view. Means if I am designing a butt weld, what should be the length of that weld? What should be the thickness of that butt weld? What will be load carrying capacity of the component if you connect two plate with butt weld? Similarly, same goes for fillet weld. So here we will study welded joint with respect to design point of view. Okay. So we'll see what is welded joint in brief manner. Next point topic is important, types of welded joint with respect to design point of view. After discussing types of welded joint, in types of welded joint we will see two type of welded joint, butt weld and fillet weld. So after that we will discuss analysis of butt weld, and after that we will start fillet weld topic, just in which we first will discuss various terminologies of fillet weld. Then we will discuss analysis of parallel fillet weld. Then we will discuss analysis of transverse fillet weld, and then we will discuss one of the most important topic in welded joint, that is eccentric loading in welded joint. Eccentric loading in welded joint. So this will be our today's lecture flow, and first topic is introduction of welded joint. Here we will only discuss what is the definition of welded joint, that you all already know, all of you already know. What is welded joint? A welded joint is a permanent joint which is obtained by the fusion of the edges of the two parts to be joined together with or without the application of pressure and a filler material. Suppose we want to connect these two plates by welded joint, or you already know what is welded joint, but here I am not explaining how to do welding, because this thing you will study in manufacturing engineering subject or production engineering subject. Suppose this is plate 1, okay, and this is plate 2. This is plate 2, and we have to connect plate 1 and plate 2 by welded joint. So what we will do, by applying the heat, what will happen? The fusion of this material of plate 1 and 2 will occur. Along with that, if you want to provide some extra filler material, you can also provide that. And due to this fusion material, these two plate will get connected, and this is permanent joint. Because after welding, you cannot separate plate 1 and 2. If you want to separate plate 1 and 2, you need to break this joint. Means this plate, and if you will break this point, means failure of this joint will occur. Without breaking, we cannot separate plate 1 and 2. Okay, means without failure, thus plate 1 and 2 cannot separated. This way, this joint is permanent joint. So welded joint is nothing but it is permanent joint. First important point, which is obtained by the fusion of material of two parts to be joined with or without the application of filler material, and with or without the application of pressure. To join this, if you want to apply, you can also apply pressure. It will help to produce welded joint. And without applying pressure also we can join this two plate. But these things, in which type of welding we apply pressure, in which type of welding we don't apply pressure, this thing you will study in production engineering. Okay, here I was just explaining what is the definition of welded joint. Here most important thing is classification of welded joint with respect to design point of view. And here we will study two type of welded joint. First is butt weld and second is fillet weld. Now we will further classify fillet weld as parallel fillet weld or longitudinal fillet weld, and second transverse fillet weld. So first I am going to discuss what is butt weld. Okay, so it is the symmetric diagram of butt weld. Now in this diagram, if you will only remember one key point, you will be easily understand what is butt weld. Here you can see in this diagram, this is suppose plate 1 and it is plate 1 2, and we have joined plate 1 and 2 through welded joint. Now this weld joint is nothing but butt weld. Why it is known as butt weld? Here you can see the plate 1 and 2, we have kept plate 1 and 2 in same plane, okay. Suppose this is plate 1, this is plate 2. If plate 1 is this, plate 2 is this, they are not in same plane. But if plate 2 is in front of plate 1 like this, it is in same plane. Now if we have kept plate 1 and 2 in same plane, and then we are joining plate 1 and 2 through welded joint, then that welded joint are known as butt weld. Yeah, it means simple definition of butt weld is nothing but the two plates which we are connecting by welded joint, if they are kept in same, only this is the key point. If they are kept in same plane, then the welded joint between them is known as butt weld. Means whenever two plates are kept into same plane, the joint is known as butt joint. Simple. Whether it is after some class, after in next chapter we will study riveted joint. In that also I will explain butt riveted joint. Definition is same. If 1 and 2 are kept in same plane, means that joint is butt joint. And for that, if we are using weld, that butt joint is known as butt weld joint. If we are using rivets, then that joint will be known as butt riveted joint. But that we'll discuss in next chapter. Today we are discussing butt weld. So we have kept 1 and 2 in same plane and welded together, and welded these two plates, then this weld is known as butt weld. Okay. If we will draw the top view of this diagram, it will nearly look like this. And suppose this is the width of the plate W. So it is the width of the plate. Now suppose and it is the front view of this, front view. So it is the front view. Okay. Now sometime can I say here the length of the weld is equal to width of the plate? Okay. If we are doing this weld in entire width of the plate, right now this diagram is given, means you can easily see here length of the weld. This is known as length of the weld, butt weld. So length of the butt weld is equal to width of the plate. But suppose examiner has only given this view. So in that case, either examiner will mention what is the length of the weld. Okay, if it is not unknown, he will mention what is the length of the weld. Otherwise, if width of the plate is given and this view is not given, and we require to solve the problem, we need to know what is the length of the weld. So we will assume that we are doing this weld in entire width of the plate. Means we will take length of the weld equal to width of the plate. But when length of the weld is not given, first point, and we cannot solve the problem without knowing the length of the plate. In that case, we will take length of the weld equal to width of the plate by assuming we are doing this weld in entire width of the plate. This thing you can remember. So this is the symmetric diagram of butt weld. Now we will do the analysis of butt weld. Now, so first I am discussing analysis of butt weld when this component which are connected by butt weld are subjected to axial force, axial tensile load P. So it is subjected to axial tensile load P. Now we need to see, due to this load P, which type of stress inducing in the weld, because we are doing analysis of weld. First before analysis I am explaining one point. This is length of the weld. Here length of the weld I am denoting as L. Right now it is equal to width of the plate, because we had done this welding in entire width of the plate. Through this view you can easily imagine. Now in this view you can see this part. If you look from this part, in this part, suppose this part I am shading and this part I am shading. This shaded portion you can see is outside the plate. Okay, because if you will do welding, it will not occur in proper manner. Means some part of weld material will go outside the plate, like this part and this part. Suppose I am denoting this thickness as a T1. Okay, this dimension is nothing but thickness of the weld. thickness of butt weld, this thickness as T2, and now I am denoting this thickness as T, thickness of weld which is inside plate, this thickness as T. Now during analysis you need to keep this point in your mind, it is very important. During analysis, if you see actual thickness of weld in this direction is T1 plus T plus T2, okay, I understood. But during analysis, whenever we will calculate stress in the butt weld, during analysis whenever we will calculate stress in the butt weld, whether that is stress is that stress which is inducing in the weld is normal stress or shear stress, that is different thing. But whenever in butt weld we will calculate stress in the butt weld, the thickness of weld which is outside this plate, like in this case it is T1 and it is T2, this thickness we will not consider. And if we are doing so this thing we will keeping ourselves on safer side. Okay, so if we are doing the designing by neglecting this T1 and T2 part, then no problem, we are keeping ourselves on safer side. But whenever we will do designing in butt weld, or whenever we will calculate stress in butt weld, the part of thickness of weld material which is outside the plate, we will not consider that thickness. Means the thickness during design which we will consider is this thickness. Right now it is equal to T, and right now it is equal to plate thickness. So if this diagram is not given, then you can take effective thickness of butt weld. I am talking about butt weld, it is not about fillet weld. Then you can take effective thickness of butt weld is equal to plate thickness if this diagram is not given. But important key point is in butt weld during analysis this thickness will not consider. Means during stress calculation, imagine this thickness is not present in the diagram. Okay, so we will only consider this thickness. And the effective thickness of weld bed which we are considering during analysis, right now it is T. Can I say this is effective thickness, because we are considering this thickness during analysis, and this effective thickness of butt weld is known as lag of butt weld. Okay, lag of butt weld. So it is nothing but lag of butt weld. Now what we will do, we will calculate stress. Now in butt weld we always calculate stress in the plane which is along length. Okay, because suppose imagine if this butt weld is breaking in along this plane, this plate 1 and 2 will get separate, means this joint will fail. So if we want that this joint should not fail, means can I say this butt weld should not break along the plane? For that, stress which you are inducing in this plane should be less than permissible stress. Yes sir, definitely. That's why in butt weld during design we will always calculate stress which is along plane, which is along length. Okay, so whenever I will take any plane, I will take that plane along length. Okay, so in welded joint we will calculate stress always in the plane which is along plane. Now in along length. Now along length, if I will draw one plane, this thickness I will consider during analysis, and along length it will be nearly like this. Now I have to calculate in this plane which type of stress inducing due to this force P. For that we need to see this force P is perpendicular to this plane or along this plane. If force P is along this plane, definitely in this plane shear stress will induce. If force P is perpendicular to this plane, so definitely in this plane normal stress will induce. So right now you can see this force P is perpendicular to this plane. Means can I say due to this force P in this plane normal stress will induce, and that normal stress will also be in tensile nature. Why? Because this force P is perpendicular to this plane in outward direction. Means due to this force P in this plane tensile stress will induce. Now what will be the magnitude of tensile stress? Suppose I am denoting this tensile stress as sigma T. And you can also say that this tensile stress is maximum tensile stress, because apart from force P no other load is acting in this plane. Okay, so whatever tensile stress is coming in this plane, that will be maximum tensile stress. And formula to calculate this tensile stress is nothing but whenever we are calculating stress due to force, we will apply formula force divided by area to calculate stress. So this force is P divided by this effective area, and effective area is nothing but thickness into length. So length of the weld I am denoting as L. Now what is the effective thickness that you need to consider? Means you can say, sir, actual thickness is T1 plus T plus T2, but not. During analysis, we will not consider T1 and T2 thickness. So effective thickness of weld, butt weld, which we are considering during analysis is T. So tensile stress which will induce in the weld is P upon T. Okay. Now during design, if you are doing the designing, this tensile stress must be less than equal to permissible tensile stress of this weld material. That will be given in the question if any unknown is coming. So it must be less than permissible tensile stress of the material. Okay. Suppose our objective is in question T and L is given. Our objective is to calculate limiting value of load P. So limiting value of load P will come a sigma Tp into T into L. Okay, this value I have got by taking equal to sign. Now actual P should be either equal to this or less than this. Why less than this? We will be on safer side when actual stress is less. That this thing I have explained many times. And when actual stress will be less, when P is less, because it is coming above side. So whatever limiting value is coming by equating this actual stress with permissible stress, the actual value of P either will be equal to this or less than this. And actual value of P should be equal to this or less than this. This why this value is also known as load carrying capacity of this component, because actual P should be either equal to this or less than this. So it is also known as load carrying capacity of this component. So if examiner is asking what will be the load carrying capacity of this component, means examiner is asking what is the limiting value of P. And to calculate limiting value of P, equate sigma T with permissible. Okay, because we are getting this limiting value with equal to sign, and into effective area, and effective area is nothing but T into L. But you need not to remember this relation. Through this calculation you can easily find this. So it is the load carrying capacity of this butt weld. Okay, analysis is very simple. Only important thing is the thickness which you need to consider. Remember that this T1 and T2 thickness will not consider during analysis. Okay, like I am solving, this is the analysis of butt weld under axial load. Similarly, now we'll do the analysis of this butt weld under shear load. Why it is shear, that you will easily understand. Right now in this direction one force F is coming, and in this direction equal and opposite force F is coming. Now see carefully. Again we will calculate stress along length, but before that, again, this thickness is T1, this thickness is T, and this thickness is T2. Again, effective thickness of butt weld is equal to T, you can see. Now we will calculate stress in the plane which is along length. So I am drawing a plane along length. This is the plane along length. Now see whether this F is along this plane or perpendicular to this plane. So you can easily imagine this F is parallel to this plane. Can I say in this diagram this force F is along the plane, and since this force F is along the plane, so can I say due to this force F, shear stress will induce in the plane. So here in the plane which we are plane of weld which we are considering to calculate stress, force F is parallel to that plane. That's why in this plane, due to this force F, shear stress will induce. Suppose I am denoting this shear stress as tau. It is shear stress in weld. Okay, because it is parallel to this plane. So it is shear stress in weld. Now whenever we are calculating stress due to force, whether it is normal stress or shear stress, in this weld analysis we'll use formula to calculate that stress, as formula will be force divided by effective area. Whenever we are calculating stress due to force, here this stress is shear stress because F is parallel to this plane. Okay, now formula to calculate this shear stress will be force divided by effective area. Right now force is F divided by effective area of this plane, and effective area is length of the plane, length of the weld is L, and effective thickness is T. So effective area is T into L. Okay, you see it is actual shear stress in this butt weld, and you can also say it is maximum because no other stress apart from this is coming in this plane. Okay, now when we are doing designing, this actual shear stress must be less than equal to permissible shear stress of the weld material. Yes sir, it will be given in the question. Otherwise examiner will give shear strength, then permissible shear stress will be shear strength upon FOS. So this actual shear stress must be less than equal to permissible shear stress of the weld material. Okay, so now whatever unknown examiner is asking, you can calculate. Okay, suppose examiner is asking what is the limiting value of F, you can calculate limiting value of F by taking equal to sign, which will come tau P into T into L. Now actual app either should be equal to this or less than this. Why? Because if we want to keep ourselves on more safer side, this actual stress should be less, for that app should be less. So to keep ourselves on more safer side, actual app should be either equal to this or less than this. Means now you can understand this parameter we can also refer as load carrying capacity of this, because actual app should be either equal to this or less than this. Okay, so it is the analysis of butt weld. It is very simple. Only all analysis is as per strength of material subject. Only difference is, only you need to remember the effective thickness which we will consider during analysis. Rest of the analysis is very easy. If you know strength of material subject, how to calculate stress, you will easily be able to solve the problem of butt weld. Okay, only point to be remembered is what effective thickness we will take during analysis. Okay, like I am solving one question. This is one welded component. Here also force P is coming. Here length of the weld is also given. Length of weld, it is typing error, is 100 mm. Now what examiner is saying, these two plates are connected by butt weld. You can see, yes sir. Permissible normal stress of weld material is given. Permissible normal stress means sigma TP is given. It is 80 megapascal. Means actual normal stress in the weld should be either equal to 80 or less than equal to 80. Okay. Now examiner asking what is the load carrying capacity of this component. Length of the weld is given. It is 100 mm. It was missed because it was typing error. So length of the weld is also given. It is 100 mm. Now first we will calculate stress in this butt weld. Now I already explained the effective thickness which you will cover will be this thickness. Suppose this thickness is T1, this thickness is T, and this thickness is T2. So the effective thickness of this butt weld which we will consider during analysis is this thickness. Okay, we'll neglect this part. We'll neglect this part which is outside of this plate. We'll neglect this red part. Now if we'll neglect this red part, effective thickness is equal to 12 mm. So first important point is effective thickness of this plate is, sorry, this weld is 12 mm. Okay. Now in this plane, which type of stress will induce? So along length, imagine a plane. It is like this. Okay, along length, because we will calculate stress in butt weld along in the plane which is along length. Now you can see this force P is perpendicular to this plane. You can easily imagine. This force P is perpendicular to this plane, and since force P is perpendicular to the plane, so due to this force P, normal stress will induce, and that normal stress will be of tensile nature because this force P is in perpendicular outward direction. So due to this force P, tensile stress will induce in the weld, and formula to calculate that tensile stress is force P divided by effective area, and effective area is force P is P, and effective area will be, I am denoting length of the weld suppose by L, which is 100 mm, and effective thickness of this butt weld is T, and if length is L, so effective area of the plane of butt weld in which stress is inducing is T into L, where T is thickness, effective thickness of butt weld, and L is length. Okay. Now this is actual tensile stress, and this tensile stress is nothing but maximum tensile stress, because no other stress apart from force P is coming in the weld. Now force P we have to calculate. Thickness of the weld, effective thickness we already know, it is 12 mm, and length of the weld is 100 mm. Now actual maximum tensile stress in the butt weld must be less than equal to permissible tensile stress, which is right now 80 Newton per mm square or 80 megapascal. So from this equation we get the limiting value of P, and it is coming after calculation. It is coming 80 into 12 into 100. It is coming 96,000 Newton. Okay. Now actual value of P either should be equal to this or less than this, because we will be on more safer side when actual stress is less, for that P should be less. So actual value of P either should be equal to this or less than this. So can I say it is the load carrying capacity of this component, because actual P should be either equal to this or less than this. So it is the load carrying capacity of this component, which is 96,000 Newton or 96 kilo Newton. Okay. So load carrying capacity of this component is 96 kilo Newton. Okay. So it is all about analysis of butt weld. Now we'll discuss fillet weld. Okay. So student, now we'll discuss fillet weld. So first I am discussing what is fillet weld. In butt weld I explained when two plate 1 and 2 are capped in same plane, then weld joint between them is known as butt weld. Similarly, now you will be easily to understand fillet weld. If two plate 1 and 2 which we are connecting by welded joint, if they are not capped in same plane, so definitely welded joint between them is known as fillet weld. So if two plate 1 and 2 are in same plane, then butt joint is known as butt weld joint. Similarly, if two plate 1 and 2 which we are connecting through welded joint are not in same plane, then weld joint between those two plates are known as fillet weld. Very simple. Here, like you can see, this is in this diagram you can imagine this is plate 1 and this is plate 2. And this is plate 1, this is plate 2. And you can see this plate 1 and 2 are not kept in same plane. And since they are not kept in same plane, welded joint between them is known as fillet weld. Like right now I have welded this two plate right this. One weld I have made in this along this line, and one weld I have made along this line. So one along this line and one along this line. So whether this is along this line, or it can be this along this line, this all joint are known as fillet weld. Why? Because 1 and 2 are not kept in same plane. So it is simple definition of fillet weld. Now this fillet weld are further classified as parallel fillet weld and transverse fillet weld. Now what is parallel fillet weld? This parallel fillet weld is also known as longitudinal fillet weld. This parallel fillet weld is also known as longitudinal fillet weld. In short, now I will write fillet weld as FW. Whenever I am writing FW, I am talking about fillet weld. Now suppose this component which are connected by fillet weld are subjected to any axial load P. Suppose it is subjected to any axial load P. If it is subjected to axial load, then only we can classify fillet weld as parallel fillet weld and transverse fillet weld. Now what is parallel fillet weld? If weld length, see the length of the weld, it is length of the weld. I am just seeing the length of the weld. It is the length of the weld. Yes sir. Right now in this diagram you can see this length of the weld is parallel to force P. If length of the weld is parallel to force P, then that fillet weld is known as parallel fillet weld. Okay. So if length of the weld is parallel to the force P, then that fillet weld is known as parallel fillet weld. This definition we can only use when this component is subjected to axial force P. Okay. So simple definition of parallel fillet weld is, in fillet weld, if weld length is, see the length of the weld, parallel to force P, then that fillet weld is known as parallel fillet weld. Very simple. So right now these two fillet weld are parallel fillet weld with respect to this load P, because it is parallel to force P. Now it is this side view of this fillet weld. From this side it will look like this. Okay. This is the weld length, this is the weld length, and it is parallel to force P. Means this fillet weld is parallel fillet weld. Okay. Through this view you can also easily imagine this. Okay. Now I will discuss transverse fillet weld. Now if force P is parallel to weld length, then that fillet weld was parallel fillet weld. Now you will easily understand what is transverse fillet weld. If force P is perpendicular to weld length, like here in this diagram you can see this is the weld length. Yes sir. And force P, suppose I am denoting this force as force P. This force P is perpendicular to the weld length. See the length of the weld. This is the length of the weld and this is force P. This is force P. You can imagine this is weld of the length, this is force P. I am bringing this in your view side, your side, it is like this. So you can see this is the weld length, this is force P, and force P is perpendicular to weld length. And if force P is perpendicular to weld length, then that fillet weld is known as transverse fillet weld. So here this fillet weld is transverse fillet weld. In this diagram also you can imagine it is this side view of this welded joint. This is weld length. See the length of the weld. It is weld length and it is force P. And force P is perpendicular to weld length. And since force P is perpendicular to weld length, this fillet weld is known as transverse fillet weld. Means simple definition of transverse fillet weld is weld length is perpendicular to force P or force P is perpendicular to weld length. Okay. So fillet weld, welded joint between two plates which are not in same plane. This is the definition of fillet weld. Now in fillet weld, if any axial force P is coming and that axial force P is parallel to weld length, then that fillet weld is known as parallel fillet weld. If that axial force P is perpendicular to weld length, then that fillet weld is known as transverse fillet weld. Okay. Now, before in starting the analysis of fillet weld, we will understand some of the important terminologies of fillet weld. Now, some of the important terminology of fillet weld. For that, we need to see this side view of this fillet weld. From this side, how this fillet weld is looking from this side. From this side, how this fillet weld is looking from this side. In this diagram, from this side. To see this, we need to make top view of this diagram. To see this, in this case, we need to make side view of this diagram. So whatever view, but we need to see from this side how fillet weld is looking. Because along this direction, only length is coming. Length of the fillet weld is suppose L. But in this side, you can see, in this side, various thickness is coming. One thickness is this, one thickness is this, one thickness is this. So this side view is important to understand various terminology of fillet weld. But before discussing various terminology of fillet weld, one important point is, if you look actual diagram of fillet weld from this side, it will nearly look like this. It is the actual diagram. It is the actual diagram. It is the actual diagram. Okay, it is the actual diagram of this fillet weld from this side. Okay. Now, but in this in actual diagram, this is the actual diagram. But during analysis, suppose this thickness is H. What is this thickness is known as, that I will explain. And this thickness is also known as H. Now, what we will do, from equal thickness from both sides. From this side it is H. From this side it is H. Now, I will join this 2 point by straight line. It will look like this. I have joined this 2 point by straight line. Now, this portion of this fillet weld is coming outside this region. So this region is region 1 and this region is region 2. So this region of fillet weld which is beyond this line, which is beyond this line, during analysis, first this region is known as reinforcement, and during analysis of fillet weld, we don't consider this region to keep ourselves on safer side. Okay, because means, can I say, we are taking actual thickness. Actual thickness is this in this direction. If I will say actual thickness of weld is this, but I am only taking this thickness during analysis. So whatever actual thickness I am taking during analysis, thickness less than this. So I am keeping myself on safer side. Okay, so there is no problem. So during analysis, to make our analysis simpler, we will not consider this part. In the same manner, in butt weld, during analysis we have not considered this thickness. Similarly, in fillet weld, when you will draw this side view, remember this is H, this is H. After that, we have joined this 2 point by straight line. The portion of fillet weld which is coming beyond this region, means this region, we will not consider this region during analysis. So during analysis, whenever I will make this side view of fillet weld, it will be like this, in which this thickness is H, this thickness is also H, and we have joined this 2 point by straight line. So during analysis, we will consider this side view of fillet weld like this. Actual diagram is this, but during analysis we will consider this diagram. This was important. Now I will explain various terminology of fillet weld. For that, I am drawing one diagram of fillet weld. Okay, along this side direction, only one terminology will come, which is L. L is nothing but length of fillet weld. Length of fillet weld. Very simple. Now understand one by one. Now this diagram is important. Now in this diagram, you can see various thicknesses coming. You can see infinite thickness. One thickness is along this direction. One thickness will be along this direction, along this, along this, along this, along this. Okay. So various thicknesses coming, in which one important thickness is this thickness and this thickness. Both thickness are same. So you can define both thickness simultaneously. This thickness of fillet weld, if you will see, this is one triangle, it is the base of this triangle, it is the height of this triangle, and both are same. So this thickness of fillet weld is known as lag of the fillet weld or size of the fillet weld, which I am denoting by H. It is my notation. It is standard notation to denote lag. So whenever I am saying lags or size of the weld, I am talking about this thickness, which I am denoting as H. So in this diagram, what is H? It is lags or size of the fillet weld. Fillet weld. Now if I will ask what is thickness of this fillet weld at angle theta, suppose this angle is theta, from leg dimension. Now you will say, sir, here two leg dimension is coming, this leg and this leg, from which leg dimension? So right now I have taken theta from this leg dimension, but you can take theta from any leg dimension, whether you want to take from this, you can take, you want to take from this theta you can take, but theta should be from leg dimension, then expression of TDS will remain same, whether you take theta from this or this leg dimension. Right now I have taken theta from this leg dimension, and I am asking what will be thickness of this fillet weld, which I am denoting as T dash, at thickness theta, at angle theta from leg dimension. Now formula to calculate that thickness is T dash. T dash is thickness of this fillet weld, thickness of this fillet weld at angle theta from one of the leg dimension. Whether you are taking from this leg dimension or this leg dimension, it will not matter. And the formula to calculate this thickness, I am not going on derivation. The formula is h upon, h is leg dimension, upon sin theta plus cos theta, where theta is angle from one of the leg dimension. For this expression you can take angle from this leg dimension also, this leg dimension also, value will remain same, but it should be from one of the leg dimension. Okay, so it is the formula to calculate thickness at an angle theta from leg dimension. Now if I want to calculate what is the minimum value of this T dash, that is important. That is because here infinite thickness is coming, all thickness are not important. Important thickness is what is the minimum value of this thickness, and the minimum value of T dash I will denote that way as T. T is nothing but minimum value of T dash. Minimum value of T dash means minimum thickness. Can I say T is nothing but minimum thickness of fillet weld? Minimum thickness of fillet weld, and this minimum thickness of fillet weld is known as throat. This is very important terminology of fillet weld. I am making star mark. I am doing star mark. What is throat? Throat is nothing but minimum thickness of fillet weld. It's very simple. Minimum thickness of fillet weld. Or why it is important? Because generally critical cross thickness is nothing but with that thickness which is minimum. That's why this terminology is very important. So throat is minimum thickness of fillet weld. Okay. Okay, or you can also say minimum value of T dash. Now at which angle minimum thickness of fillet weld will come? So for that you, if you want to find at which angle T dash will be minimum, because that minimum value of T dash is known as throat. For that you need to differentiate this term T dash with respect to theta, because here variable is theta, and you need to equate with 0. You will get T value of theta at which T dash will be minimum. But I am not going on derivation. Or okay, you have to remember that this throat minimum value of thickness will come at angle theta equal to 45 degree. I am not going on derivation. So if you want to find throat thickness, how you can find? In the formula of T dash put theta equal to 45 degree, because at theta equal to 45 degree means at angle 45 degree from any of the leg dimension, whether you take from this or this, T dash will be minimum, and that minimum thickness is known as throat thickness. Now here in this relation, if you will put theta equal to 45 degree, the expression of T dash will come h upon root 2. After putting you can check h upon root 2. Means can I say this formula is important? The formula to calculate throat thickness is nothing but h upon root 2, or this relation is very important, you need to remember this. Okay, what is h? H is leg dimension of fillet weld or size of the fillet weld. Okay, this thickness is h, leg of the dimension. What is T dash? T dash is thickness of fillet weld at any angle theta from leg dimension, whose formula is this. What is throat? Throat is minimum thickness of fillet weld. Throat is minimum thickness of fillet weld, and formula to calculate throat is, you need to remember this formula directly, h upon root 2. And at which angle we are getting throat? At angle 45 degree or from any of the leg dimension. Okay, and this is minimum thickness of fillet weld, whose formula is h by root 2. So these are the some general terminology of fillet weld. L is length of fillet weld. Now in this view various thickness was coming, in which this thickness is h, which is leg or size of the fillet weld. At thickness at angle theta from any leg dimension, formula to calculate their thickness is this. and minimum value of T dash or minimum thickness of fillet weld is known as throat, and formula to calculate throat is h by root 2, where h is leg or size of the fillet weld, and we will get minimum thickness, that is we will get throat thickness at angle 45 degree from one of the leg dimension. So these are the some general terminology of fillet weld. After understanding this, we will start the analysis, we will start the discussion of analysis of parallel fillet weld. Okay. So student, now we will discuss the analysis of parallel fillet weld. What is parallel fillet weld? That I have already explained. Whenever weld length is parallel to force P, that fillet weld is known as parallel fillet weld. And in parallel fillet weld, the first case we will discuss is symmetrically loaded parallel fillet weld. What it means? Suppose is this top weld is weld 1 and this bottom weld is weld 2. Both weld are parallel fillet weld. If you will see the length of weld 1, it is parallel to force P, means it is parallel fillet weld with respect to this load. If you see length of weld 2, it is also parallel to force P, means it is also parallel fillet weld with respect to load P. Right now, the cross, suppose this plate is plate A and this plate is plate B. Right now the cross section of plate B is symmetric. Cross section of plate B is symmetric means suppose it is a rectangle cross section. Rectangle cross section means cross section of plate B is symmetric. And if cross section of plate B is symmetric, right now we are discussing axially loaded case. Axially loaded means this load P is passing through the longitudinal axis of plate B. And since plate B is a symmetric cross section, can I say in this case this distance and this distance will be equal? Because longitudinal axis will come exactly at midline, because this cross section is symmetric. Suppose this distance is y, so then this distance will also be y. So it is symmetrically loaded case. Now in symmetrically loaded case, we'll take the length and leg of each weld exactly same. Means it is one of the key point. Why I am taking same that I will explain. But in parallel fillet weld case, whenever force P is acting, and if distance of force P, you can see if this distance is y, means distance of force P from top weld is also y. Distance of force P from bottom weld is also y. If both distance are same, in that case we will take weld 1 and weld 2 identical. Identical means length and leg of both weld will be same. If length of weld 1 is L, then length of weld 2 will also be L. If leg dimension of weld 1 is h, then leg dimension of weld 2 will also be h. Means both are identical. Why I am ensuring this? Because right now in this case we want only in weld only stress due to force should come. We want in weld in this case we want in weld no stress due to movement should come. Okay. If stress due to force is coming, whether it is normal stress or shear stress, that is different thing. But whenever in our weld stress due to force will come, we will name that stress as primary or direct stress. What is primary or direct stress? What is primary or direct stress? Whether it is shear or normal, that is different thing. But what is primary or direct stress? It is the stress which is coming due to direct force. It is the stress which is coming due to direct force. Okay, I will explain through diagram also. Now, but second one is B is secondary or indirect stress. Now, what is secondary or indirect stress? You can write this by giving note point. What is secondary or indirect stress? Whether it is normal or shear, that is different thing. But secondary or indirect stress is the stress which is coming due to movement. And generally due to movement, more stress induces as compared to force. Okay. So primary or direct stress is stress which is coming due to force. Secondary or indirect stress is the stress which is coming due to movement. Now in this component, force P is coming. Means it is 100% sure in weld primary or direct stress will come, because force is acting means primary or direct stress will come. That is 100% true. But here we can ensure one thing, that no secondary stress is coming. Okay. So here, because we cannot avoid that no primary stress is coming, because if direct force P is acting means primary stress will come. But here we can ensure one thing, that no indirect or secondary stress should come in the weld. And if we want, whenever this weld is subjected to any force, and if we want no indirect or secondary stress should come in the weld, for that the line of action of this force P should pass combined centroid of the weld. The line of action of force P should pass from the combined centroid of weld. If line of action of force P is passing through the combined centroid of weld, in that case no secondary stress will induce in the weld. But if line of action of weld is not passing through the combined centroid of weld, then in that case secondary stress will also induce in the weld. I am explaining this through diagram. Suppose just for understanding, this is weld 1 and this is weld 2. Okay, and just imagine it is the combined centroid of this weld. How we have located, that is different thing, but imagine this is the combined centroid of this weld. And right now line of action of force P is this. Means you can see right now line of action of force P, you can see right now line of action of force P is not passing through the combined centroid of this weld. Suppose its perpendicular distance from this combined centroid is small e, just for understanding. Now before calculating the stress within the weld, it is weld 1, it is weld 2, and it is the combined centroid of both the weld. Now to calculate stress in the weld, first we need to transfer this force P in the combined centroid of weld. And when you will transfer this force P in the combined centroid of weld, here one direct force P will come, means primary stress will come, it is 100% sure, whether it is passing through line of combined centroid of the weld or not passing through combined centroid of the weld. But right now if this force P is not passing through the combined centroid of the weld, its perpendicular distance from combined centroid is E. So when you will transfer this force P in combined centroid, here one moment will also come P into E, and right now its direction will be anti-clockwise if diagram is like this. Yes sir. Means here due to force P, primary stress will induce or direct stress will induce, whether it is shear or normal, that is different thing. Okay, but here one moment P into E is also coming, and due to this secondary or indirect stress will induce. Means if line of action of force P is not passing through the combined centroid of the weld, in that case secondary stress will also induce in the weld. But if here we can ensure that line of action of force P is passing through the combined centroid of the weld by proper maintaining the length of the weld, if we can ensure that, means in that case no secondary stress will come in our weld. Primary stress will come in that case also, but no secondary stress will come in the weld. And that thing we can always ensure in case of parallel fillet weld. And how we can ensure? By ensuring that line of action of this force P is passing through the combined centroid of the weld. Now if the case is of case when it is symmetrically loaded means this distance and this distance both are same. In that case, how we can ensure that line of action of this force P, this is the line of action of force P, how we can ensure that line of action of force P is passing through the combined centroid of the weld? For that we will take length of both this weld equal. First we will place weld in both sides, because if here only one weld we will place, here one weld, then combined centroid will come at this location, means line of action of force P will not pass through combined centroid. If only top weld is attached, bottom weld is not attached, means here secondary stress will also come in the weld. So to ensure line of action of this force P is passing through combined centroid, first we need to take two parallel fillet weld, one above this and second below this line. Now to ensure that combined centroid is exactly coming in this line, we need to take the length of both top weld and both weld exactly same when this distance y is same. Means if distance of load P from top weld is y and distance of load P from bottom is weld is y, both are equal. In that case, to ensure that combined centroid is lying in this line, for that we need to take length of both weld equal. So in symmetrically loaded case, we will always take length of both weld exactly equal, whether examiner has mentioned or not, to ensure line of action of force P is passing through combined centroid, such that if we are ensuring this, it means no secondary stress will induce in our weld. So right now in this diagram you can see right now line of action of force P is passing through combined centroid. Why? Because length of both weld 1 and 2 are same, means combined centroid will exactly come in midline. And right now line of action of load P is also coming in midline, means right now line of action of force P is passing through combined centroid. It means here primary or direct stress will come, that we will understand how to calculate that. But here can I say now no indirect or secondary stress will induce? And why you can conclude this? Because if you transfer this force P in combined centroid, direct force P will come, but no moment will come, because the perpendicular distance of force P from combined centroid is 0. So here if you will transfer this force P in combined centroid, only force P will come, means only primary stress will come, no secondary stress will come. Now we need to calculate, due to this force P, which type of primary stress will come in the weld, whether it will be shear or normal or both will induce. And ultimately we have to calculate what will be maximum value of that stress, because critical value is maximum value. Okay. So for that, right now this force P is parallel to weld length. So suppose I had drawn the diagram of one fillet weld, and suppose in this fillet weld any resistance R is coming, just for understanding, which is parallel to weld length. Here you can see this resistance R is parallel to the weld length. Now we need to calculate, due to this force R, what type of stress will come in this weld. Okay, and whenever we will calculate stress in the weld, we will take the plane of weld along length. Why we will always take plane along length? Because whenever any fillet weld will break along length, the plate 1 and 2 will, or plate A and B will get separated with each other. So whenever in weld, whether it is butt weld, fillet weld, we are calculating stress, we will calculate stress in the plane which is along length. Now suppose I am calculating stress in this plane. It is one of the lag plane. This length is L and this thickness is lag dimension. So it is, you can see, one of the lag plane. And this lag plane, we have in fillet weld we have two lag plane. One is this and one is this. So here length of the weld is L. Always length of the weld will remain same, which is L. But here the thickness, because in fillet weld lot of thickness are involved. So right now I am taking lag thickness and this lag thickness. Now if I want to calculate in this plane, due to this force R, when it is parallel to weld length, which type of stress will induce? For that we need to see this resistance R is parallel to this plane or perpendicular to this plane. So you can easily imagine this R is coming in this direction, that is Z direction, and this bottom plane is like this. Means you can easily imagine this resistance R is parallel to the plane. And with resistance R is parallel to the plane, means can I say in this plane, due to this resistance R, shear stress will induce. And whenever shear stress is inducing, suppose I am referring this plane as plane A. So shear stress at plane A will be resistance R divided by area of plane A, because whenever we are calculating stress due to force, we will always divide resistance divided by area. This formula we will use. And area of this plane A is HL. Okay. And which type of stress is inducing? Shear stress inducing. Now similarly, this we have talked about bottom plane, this plane. Now suppose if you want to calculate stress in any at any thickness, suppose I want to calculate stress is this plane, and at this plane thickness is T dash, and we already discussed the formula to calculate T dash. It is H upon sin theta plus cos theta, where theta is angle from any of the leg dimension, whether this dimension and this dimension. Okay, and through after calculating stress at T dash thickness, we will get the general formula of stress, because we already know T dash formula for all time or for all value of theta. Okay, if you want to calculate stress at throat, put value of theta equal to 45 degree, and at throat thickness is nothing but it is equal to h by root 2, because in the formula of T dash, if you put theta equal to 45 degree, you will get T equal to h by root 2. Okay, so if you have calculated stress in this green plane, which is where thickness is T dash, means now you have calculated the formula to calculate stress in any of the plane by taking any thickness. Just you have to put the theta of that plane. Okay, so suppose I am going to calculate stress at this T dash plane. I am referring as this as T dash plane. Okay, so how to calculate shear? Again, first we need to see in this T dash plane, means in this green plane, which type of stress will come due to resistance R when it is parallel to the weld length. So here you can again see this resistance R is also parallel to this green plane, because green plane is like this and resistance R is like this, means again resistance R is parallel to the green plane. And since resistance R is parallel to the green plane, again shear stress will induce in the green plane, and formula to calculate that shear stress will be resistance R divided by area of green plane, that is T dash plane, and this area is nothing but T dash L. Similarly, if you want to calculate shear stress at throat, because if stress at T dash thickness plane is coming shear stress, means here stress in each plane is shear stress, and formula to calculate that shear stress is resistance divided by area of that plane, and in that area length L is constant, only this T dash will change. So if you want to calculate shear stress at throat, it will be R divided by TL, and T is nothing but H by root 2. Okay, we already know. So it is shear, means can I say in case of parallel fillet weld, whenever force is parallel to the weld length, in each plane of fillet weld shear stress will induce, whose formula to calculate is resistance divided by area of the plane. If you want to calculate shear stress at leg plane, it will be HL. At T dash plane, it will be T dash L. And if you want to calculate at throat plane, it will be TL. And if in each plane shear stress is inducing, we need to calculate what is the critical shear stress. And shear stress, critical value of shear stress will be that value of shear stress which is maximum. And out of these values, you can see this is maximum. Why it is maximum? Because in all the formula, top side is constant, which is equal to R. Okay. Bottom value is changing due to thickness because length is constant. Now, whenever bottom value is minimum, then in that case this stress will be maximum, and bottom value will be minimum where thickness is minimum, and minimum thickness is known as throat. So here can I say maximum shear stress will induce at the throat, okay, due to force. And formula to calculate that maximum shear stress in case of parallel fillet weld is force divided by total throat area. Right now, if this for this the total throat area is TL and force is R. So formula to calculate shear stress at throat will be resistance R divided by TL, and that is the formula of maximum shear stress. Now conclusion is, ultimately on welded joint our objective is to design, and for design we will only calculate stress of critical cross section. And in case of parallel fillet weld, critical cross section, can I say critical section is throat, because in that section stress is maximum. Okay, ultimately I will discuss various cases of welded joint, and in all cases ultimately we will reach to the throat plane. Means throat plane will be most important plane during the analysis of welded joint. But right now forget about other cases, only focus on parallel fillet weld. So in parallel fillet weld, the critical section is throat plane. So whenever we are calculating shear stress in parallel fillet weld, we will only calculate shear stress in throat plane. We need not to bother about what shear stress will induce in leg plane, what shear stress will induce in T dash plane. That I have already discussed, that in all plane, in case of parallel fillet weld, shear stress will induce. Formula to calculate that shear stress is force divided by area of the plane in which we are calculating shear stress. If you are calculating shear stress in leg plane, it will be leg area. If you are calculating T dash plane, it will be T dash L, means T dash area plane area, that is T dash into L. If you are calculating in throat area, it will be, we will divide R by throat area, which is TL. Okay, but ultimately out of this three value, important value is this value, which is coming as the throat because it is maximum. So we need not to bother about other shear stress which is coming in other plane. Examiner will never ask about shear stress in other plane. If he is asking, that I have already discussed. Ultimately, whenever examiner will say in case of parallel plate weld, what shear stress is coming in the weld, he is talking about shear stress which is coming in the throat. Means if it is not mentioned in which plane we have to calculate shear stress, we will calculate throat at throat. What shear stress is coming in other plane, that for that we need not to bother about. We will only focus on throat plane. Okay. So can I, if I will summarize all this thing, in case of parallel fillet weld, whenever stress is coming only due to force, that is primary stress is coming, and that force is parallel to weld length, then the shear stress will induce in our weld, and we will always calculate shear stress in the throat, and whatever shear stress is coming in the throat, that will be maximum shear stress if only force stress due to force is acting, because this is primary shear stress because it is due to force. But if no other moment is acting in the weld, and right now no other moment is acting because we are discussing the case when no secondary stress is coming, because line of action of force P is passing through combined center. So if stress due to only force is coming, then this primary stress which is coming at the throat will be maximum shear stress. And formula to calculate this primary shear stress is total force. Write down total force for this diagram is R divided by total throat area. It is total force due to which primary shear stress is coming, divide by total throat area. Means during analysis we will only calculate shear stress at the throat. We don't have to bother about the shear stress which is coming in other plane. And so we will multiply this force divide by total throat area. For this diagram it is TL. For this diagram it is TL. Okay. Okay. Now I am coming back to this our original case. Right now this force P is parallel to the weld length, means it is the case of parallel fillet weld. And since this force P is passing through the combined centroid of the weld, means here only primary stress will come. And that primary stress, whenever force P is parallel to weld length, its nature will be shear. That I have already discussed. You need to remember this now. So due to force P, can I say primary shear stress will come in the weld? Why primary? Because it is coming due to force. And why shear? Because whenever force P is parallel to weld length, shear stress will induce. Now formula to calculate this primary shear stress is, I am denoting this as tau dash, or you can also simply say as tau. Okay, but in upcoming lecture, in upcoming topic, I will also discuss stress which is coming due to movement. So what notice I am taking for stress which is coming due to force, that is primary. For primary stress, I will use dash, one dash. But for secondary stress, I will use double dash. So since it is primary stress, that's why I used dash. And formula to calculate this primary shear stress in the weld is, whenever I am saying simple primary shear stress in the weld, due to that means I am calculating primary shear stress in the throat. Formula to calculate this primary shear stress is total force. Right now total force is P. Divide by total throat area. Okay, and total throat area. So here this combined centroid is for both weld 1 and weld 2. So we have to multiply total throat area of weld 1 plus weld 2. Now length of weld 1 is L and length of weld 2 is also L. Throat of weld 1 is T and throat of weld 2 is 3. If examiner has given the value of lag dimension, you can calculate throat. So throat area of weld 1 is TL. Yes sir. And plus throat area of weld 2 is, right now it is also TL, because length of both weld is same, because we are talking about symmetrically loaded. And in symmetrically loading, to ensure force P is passing through combined centroid, we will take length of both weld exactly same. So it is, and it is maximum shear stress right now, because no other stress is coming in the weld. It is primary shear stress at the throat due to force P, and since force P is parallel to weld length, formula to calculate this is total force divided by total throat area, and it is maximum shear stress because no other stress right now is coming in the weld. So the formula is total force P divided by 2TL. Okay. Okay, you need not to remember this, you can also only remember conclusion. If stress is only coming due to force P which is parallel to weld length, only primary shear stress will come, whose maximum value will be at throat, whose formula and formula to calculate that maximum shear stress is total force divided by total throat area. Right now total force is P, divided by total throat is 2TL. And why no secondary stress is coming? Because we have ensured that line of action of force P is passing through combined centroid of the weld, and in case of parallel fillet weld, that we will always ensure. Okay. And whenever now examiner is asking to find some unknown, so definitely examiner will give the value of permissible shear stress. Why permissible shear stress? Because right now it is subjected to shear stress. Okay, or examiner can also give value of shear strength and factor of safety, and shear strength upon FOS will be the value of permissible shear stress. So suppose permissible shear stress of this weld material is tau P, so this actual maximum shear stress, either it should be equal to tau P or less than tau P. Okay, tau P. So for design you can equate it with tau P. Okay, to find its limiting value. So it is the analysis of symmetrically loaded parallel fillet weld. Very simple. Okay. If examiner has given the value of throat thickness or leg dimension, if it is given directly, no problem. If not given directly, examiner will definitely draw this diagram, side view. It is a side view of this diagram. Through side view, we can see this portion of fillet weld, and in this fillet weld, this thickness is leg. Now, through this diagram, suppose this is plate A and this is plate B. You can see, in this case, the leg dimension, that is H, is exactly equal to the thickness of plate B, which I am denoting as TP. So if the thickness of plate B is given, can I say leg dimension given? If directly examiner has mentioned the value of leg dimension or throat, means we need not to draw this view. But if leg dimension is not directly given, so examiner will definitely give this view. If we require the we need to know what will be the value of leg dimension or throat to solve the problem. So definitely examiner will give this view, and through this view you can conclude this leg dimension is exactly equal to the thickness of plate B. But suppose in exam this view is not given, because might be diagram can be like this also. If actual diagram is this, leg dimension H will be less than TP. Okay, but generally we will always cover entire thickness of plate B. Means H will be equal to TP, because it is more safer as compared to this. But suppose examiner has not given this diagram, but in wording, in question in wording it is mentioned that thickness of plate B or thickness of the plate is 10 mm say, and we cannot solve the problem without knowing the value of leg dimension or throat. So in that case you can imagine that we are covering the entire thickness of this plate B, and you can automatically take value of H equal to the thickness of plate B, that is TP, if this view is not given, and we cannot solve the problem without knowing the value of H. And if you know the value of H, you can easily calculate the throat thickness. Throat is T equal to H by root 2, because in the formula of stresses throat area is coming, leg area is not coming. So to calculate stress, throat area is more important than leg area. So if leg dimension is given, you can calculate throat, and you can calculate primary shear stress, and for design it should be less than equal to permissible shear stress of the weld material. Okay, based on this I am discussing one question. It is the question, this welded component is subjected to this axial load P 60 kilonewton. Suppose I am denoting this load as P, and it is 60 kilonewton. In Newton it will be 60,000 Newton. Permissible shear stress of the weld is 100 megapascal. Suppose I am denoting permissible shear stress as tau P, it is 100 megapascal. Now we have to calculate required length of each weld. See the question carefully. Required length of each weld. So here length of top weld and bottom weld both are L. So required length of each weld means we have to calculate L. But suppose examiner asking what is the total length of weld. So total length of weld is 2L. So read the question carefully. Here we have to calculate required length of each weld, that is L. Now why we have taken, here examiner has already mentioned, but why we have taken taking length of each weld exactly same? Because right now it is symmetrically loaded. Why symmetrically loaded? You can see distance of this load P from top weld is 60 mm, and from bottom weld it is also 60 mm. Okay, and since it is symmetrically loaded, so to ensure no secondary stress is coming in our weld, for that this line of action of force P should pass through combined centroid of the weld. And right now again combined centroid will also of weld will also be in this midline. Why? Because length of both weld are same. Okay, and since length of both weld is same, the combined centroid will lie in this line, means line of action of force P is passing through combined centroid, means only primary stress will come. Now if only primary stress will come, what will be its value? So first see, length of weld is L. Now what is the throat of weld? So through this diagram you can see this is the leg dimension of weld, which is exactly equal to this plate thickness, which is 15 mm. So right now leg dimension H is 15 mm. So you can calculate throat, because to calculate stress, throat thickness is more important as compared to leg thickness. And if you calculate throat thickness, it will come, I am calculating, just wait for 1 minute, 1 second, I am opening the calculator. Okay, this throat thickness will come, throat will be equal to H by root 2, and H is 15 mm divided by root 2. If you solve this, it is coming 15 divided by root 2, it is coming 10.6066 mm. So it is the value of throat. Now since our weld no secondary stress is coming, because line of action of force P is passing through combined centroid, so we will calculate only primary stress. And right now force P is parallel to weld length, and whenever force P is parallel to weld length, primary shear stress will induce. So due to force P, primary shear stress will induce, because force P is parallel to weld length, primary shear stress will induce. Now formula to calculate this primary shear stress is, suppose I am denoting this as tau dash. Formula to calculate this primary shear stress is total force divided by total throat area, because this is the value of critical shear stress due to force. Okay, we will always calculate primary shear stress by dividing force P divided by throat area. That I have already explained. So primary shear stress will be total force P divided by total throat area. Right now total force P is 60,000 Newton divided by total throat area. So if I will write the expression of total throat area, what will be its expression? Throat area of weld 1. Suppose this is weld 1 and this is weld 2. So throat area of weld 1. Throat of weld 1 is T and length of weld 1 is L. So throat area of weld 1 will be T into L. Similarly, throat area of weld 2. Throat of weld 2 is also T and length of weld 2 is also L. So throat area of weld 2 will be TL. Means total throat area in this case is 2TL. So divide by total throat area 2TL, in which value of T is given, L is unknown. So tau dash is coming 60,000 divided by twice of throat, which is 10.6066 into L. Okay. And this is maximum shear stress. Why this is maximum shear stress? Because right now no other stress other than primary stress is coming in the weld. And if no other means no secondary stress is coming in the weld, so this primary shear stress will be overall maximum shear stress. Now for design, this overall maximum shear stress must be less than equal to permissible shear stress of the weld material, which is given in the question. So this maximum shear stress, that is 60,000 divided by 2 into 10.6066 into L, must be less than equal to permissible shear stress, which is 100. So if from this you can calculate L, limiting value of L. Okay, and it is coming to calculate limiting value, use equal to sign. It is coming to 100 into 2 into 10.6066 divided by 60,000. 60,000 divided by 2 divided by 10. Do calculation correctly. Divided by 10.6066 divided by 100. You can check calculation. Limiting value of LK is coming 28.284 mm. It is the limiting value of L, that is length of each weld. Okay. Now suppose but examiner is asking answer with non-equal sign. So to apply non-equal sign, always ensure to be on more safer side. Actual stress should be less, and when actual stress will be less when L is more, because it is coming below side. So actual value of L either should be equal to this or greater than this. Okay. But to give the value of limiting value, use equal to sign, and with equal to sign it is coming 28.284 mm. So limiting length of each weld is 28.284. Okay. So it is the analysis of symmetrically loaded parallel fillet weld. Okay. Now we'll discuss the next case in parallel fillet weld, and that next case is unsymmetrically loaded parallel fillet weld. It is also easy. If you understood symmetrically loaded, you will be able to easily understand this case also. Unsymmetrically loaded means, if here you will see right now this is the force P, and right now this plate B, suppose this is plate A, suppose right now I am denoted this plate as plate 1 and this is plate 2. Now here you can see this plate 2 is not symmetric. And if this plate 2 is not symmetric, suppose it is the centroid of plate 2, it is not centroid of weld. Weld is there. I am talking about centroid of weld 2. So definitely centroid of weld 2 will not be exactly mid-line. Why? Because this plate 2 is not symmetric. And due to this right now this force P is not passing exactly at the mid-line of this plate 2, because this plate 2 is not symmetric. So right now this distance of this load P from this top line is Y1. And this distance is Y2, and now right now you can see this Y1 is not equal to Y2. This Y1 is not equal to Y2, and if Y1 is not equal to Y2 means ultimately you can see this is top weld. So this is top weld A, this is bottom weld. I am denoting this as B. You can see this top weld A, the perpendicular distance of load P from top weld A is Y1. The perpendicular distance of this load P from bottom weld B is Y2, and right now Y1 and Y2 are not equal. And if Y1 and Y2 are not equal, that case is known as unsymmetrically loaded parallel fillet weld. Now in unsymmetrically loaded parallel fillet weld, if you will take length of both weld equal, right now both are not equal, but suppose if you are taking length of both weld, means top weld and both weld are equal, in that case combined centroid of weld will come exactly at the midline. This distance, if length of both weld are same, And if combined centroid is exactly coming at midline, but right now line of action of force P is not coming at midline. So definitely in that case, this force P will not pass along from the line of action of load P will not pass from the combined centroid of weld. And in that case, apart from primary stress, secondary stress will also induce in the weld, which is not good thing. But here also you can ensure that no secondary stress is coming in the weld. How you can ensure? By ensuring that line of action of force P is passing through this combined centroid. Now question is, how you can ensure in unsymmetric case line of action of force P is passing through combined centroid of weld? Means in this line combined centroid of weld should come. For that what we will do, will not take length of both weld exactly same. Suppose I have taken length of top weld equal to L1. Suppose I have taken length of bottom weld is equal to L2. Now question will come in your mind, what should be the relation between L1 and L2 to ensure line of action of force P is passing through combined centroid? Means what should be the value of L1 and L2 to ensure in this line combined centroid is coming? For that we need to maintain a relation. First I am drawing this diagram. Suppose this is top weld, and if you want you can draw this diagram separately also. Bottom weld, length of top weld is L1, length of bottom weld is L2. Right now line of action of force P is passing through this line, whose perpendicular distance from top weld is Y1. If I am denoting this length as L1, I am denoting this length as Y2. Whose distance from bottom weld is Y2. And along this line force P is passing. If we want in our weld no secondary stress should induce, for that in this line combined centroid of the weld should come. Means combined centroid of the weld should lie in this line. Now to ensure that, we need to ensure one equation. To ensure combined centroid of weld, which I am denoting as CW, is, or you can also write like this, to ensure line of action of force P is passing through combined centroid of the weld, that is CW. We need to satisfy one equation which is L1 Y1. I am not going derivation, I am directly writing the relation, equal to L2 Y2. This relation is important. L1 is length of top weld into Y1. Y1 is distance or perpendicular distance of this force P from top weld, and that should means product of L1 and Y1. That should be equal to L2 Y2, where L2 is length of bottom weld and Y2 is perpendicular distance of force P from bottom weld. Very simple. Okay, and you can also match this relation for symmetric loading case also. In symmetric loading case, can I say Y1 and Y2 both are equal and equal to Y? And if you will apply same relation, L1 Y1 equal to L2 Y2, and in symmetric load Y1 and Y2 are same, so you will come into conclusion L1 and L2 equal to should also same, and that relation we have maintained in symmetrically loaded. Okay, we have taken the length of both weld exactly same. But if it is not symmetrically loaded parallel fillet weld, in that case we need to take value of length L1 and L2 different. We will not take both values same. Now what relation we need to maintain? We need to maintain this relation. And if we are taking value of L1 and L2 by maintaining this relation, means we are ensuring line of action of force P is passing through combined centroid, and that we will always ensure, because in parallel fillet weld we don't want any secondary stress should come in our weld. So this relation we will always ensure. Okay, so it is the one relation between L1 and L2, and you need to remember this relation. Okay, now if we are ensuring this relation, and in this case we will always ensure this relation, it means, can I say no secondary stress will come in our weld, only primary stress will come. And since force P is parallel to the weld length, means primary stress will be primary shear stress, because whenever force is parallel to the weld length, then stress due to force in the weld will be primary shear stress. Okay, so here only stress due to force P will come, means can I say here only primary stress will come, no secondary stress will come. Okay, why only primary stress will come? Because when you will transfer this force P in combined centroid, only direct force P will come, no moment will come. Okay, now what will be the value of primary stress? So here due to force P, primary shear stress will come. Why primary shear stress? Because whenever force P is parallel to weld length, then due to force in weld, always shear stress will come. That will be known as primary shear stress. Now formula to calculate this primary shear stress I am denoting as tau days. Formula will remain same. Due to force P, if it is parallel to weld length, the formula to calculate primary shear stress is total force divided by total throat area. Means formula will be total force P divided by total throat area. So right now total force P is P and total throat area. Right now in this diagram, throat area of weld 1 is L1T. L1 is length. I am denoting leg dimension of weld as H and throat dimension as T. Okay. So throat area of weld 1 will be L1T. Throat area of weld 2 will be L2T. So total throat area is L1 plus L2 into T. Okay. And since no secondary stress is coming, so can I say in this case this primary stress is nothing but overall maximum shear stress, and is this overall maximum shear stress should be less than equal to permissible shear stress of weld material. To find limiting value, you can equate this with permissible shear stress. Okay. So here two relations are important. To ensure line of action of force P through passing through combined standard, L1 Y1 must be equal to L2 Y2. This is one of the relation. Second, since line of action of force P is passing through combined standard, means only primary stress will come, and since force P is parallel to weld length, that primary stress will be primary shear stress, and formula to calculate primary shear stress is total force P divided by total throat area. Very simple. And it will be overall maximum shear stress because no other stress is coming in the weld, which should be less than equal to permissible shear stress of the weld material. Okay, so here these two equations are important. So it is the analysis of unsymmetrically loaded parallel fillet weld. Based on this concept, I am solving one question. It is the question. It is MSQ, means more than one option can be correct. An angle plate, this is angle plate, is welded to a steel plate by means of fillet weld. Angle plate is subjected to axial force of 100 kilonewton. This is axial load. I am denoting this load as P. If we will convert this in Newton, it will be 100,000 Newton. I also drawn this diagram separately. It is axial force P in kilonewton. If you will convert this in Newton, it will be 100,000 Newton. Now, permissible shear stress of weld material is 50 megapascal. It is permissible shear stress, means actual maximum shear stress should be equal to this or less than this. To find limiting value, we will equate actual maximum shear stress with permissible value. Now, which one or more of the following options are correct? MSQ, so we have to see all the options. And ultimately, in this question, examiner asking length of top weld and length of bottom weld. Means ultimately in this question, we have to find length of top weld also and length of bottom weld also. For that, first we will ensure, since it is the case of parallel fillet weld, and suppose length of top weld is L1 and length of bottom weld is L2. Okay. Now, leg of the weld is already given. How? This is the leg of the weld. This is the leg of weld, and you can see right now leg dimension is equal to this thickness. Okay, through this diagram you can find this, and this leg dimension is equal to this thickness, and this thickness is nothing but tan root 2 mm. So here can I say leg of the weld is H is 10 root 2 mm, and if leg is given, you can calculate throat, because in welded joint during stress analysis throat dimension is important, and throat is nothing but H by root 2. H is 10 root 2 divided by root 2. So value of throat is coming exactly equal to 10 mm. Now first we will ensure that this line of action of force P is passing through combined centroid of weld. For that we need to maintain a relation L1. What we will do, we will this distance of this load P from top weld, we will denote, if I am denoting this distance as L1, I will denote this distance as Y1. Similarly, distance of load P from bottom weld, I am denoting, if I am denoting this length as L2, I will denote this length as distance as Y2. Now you can see from this diagram, this Y1, this distance is given in the question. It is little bit typing error. Actually this distance is 50 mm, and this whole height is 150 mm. So if it is 150, it is 50. So definitely this distance will be 150 minus 50, that is 100 mm. All dimension I am taking in mm. So distance of this line or load P from top weld is Y1, which is equal to 100 mm. So value of Y1 is 100 mm. Now Y2 is this distance, which is already given in the question. It is 50 mm. Now to ensure line of action of force P is passing through combined centroid, we need to maintain a relation. That relation is L1 Y1 must be equal to L2 Y2. Yes sir, L1 Y1 is 100, it must be equal to L2 Y2 is 50. So from this relation is coming L2 should be equal to twice of L1. This is one important question. So L2 should be equal to twice of L1, means L2 should be more than L1. Okay. Now in question, permissible shear stress is given. So we will calculate the formula of maximum shear stress, that should be less than equal to permissible. Now here, since force P is passing through combined centroid of the weld, means so can I say here only primary stress will come in the weld, and which is coming due to force P, because no secondary stress will come. Now force P is parallel to weld length, and whenever force P is parallel to weld length, nature of primary stress will be shear. So can I say here primary shear stress will induce in the weld due to force P. Now formula to calculate that primary shear stress is total force divided by total throat area. So total force is P, whose value is 100,000 Newton, divide by total throat area. Here I am writing the expression of total throat area. Throat area of weld 1 is L1T. Throat area of weld 2 is L2T. So total throat area will be L1 plus L2 into T, where throat T is given, it is 10 mm. So total throat area will be 10 into L1 plus L2. So primary shear stress is total force divided by total throat area, which is L1 plus L2 into T, and T is 10 mm. And since no secondary stress is coming in the weld, so can I say in this case this primary shear stress is nothing but overall maximum shear stress, and this overall maximum shear stress must be less than equal to permissible shear stress of the weld material. Okay, so this 100,000 divided by L1 plus L2 into 10 must be less than equal to permissible shear stress, which is 50 megapascal. Now to find limiting value, we will use equal to sign, and if you will use equal to sign, you will get the value of limiting value of L1 plus L2, and it is coming 100,000 divided by 10 divided by 50. It is coming L1 plus L2 equal to 200 for limiting value. Actual L1 plus L2 should be either equal to this or more than this, but this is limiting value. Suppose I am denoting this equation as equation 2. Now we have two equations. One, L2 should be equal to 2L1, and another L1 plus L2 equal to 200. So two equation, two unknown we can calculate. So how we can calculate? From this equation I am putting L2 equal to 2L1 in this equation. So it will be L2 is equal to 2L1. So it is already L1 plus L2 is equal to 2L1. That should be equal to 200. So we will get the value of L1. It is coming 200 divided by 3. That is 66.667 mm. 66.667 mm. So we have got the value of L1. Okay. Now L2 we already know, L2 is equal to twice of L1, and if you will put the value of L1, which is 66.667, we will get the value of L2, and L2 is coming twice of 66.667, and it is coming 133.333 or 334 mm. Okay, so it is the value of L2. Okay, so L1 is 66.667 and L1 is length of top weld. So length of top weld is 66.667 top weld. So option A is incorrect. It is 130. Option C is correct because length of top weld is 66.667 mm. Now second one, examiner is asking about length of bottom weld, which is L2, and length of bottom weld is 133.334 mm. So bottom weld, this option is incorrect. D is correct. Length of bottom weld is 133.334 mm. So for this question, option C and option D are correct. So we have discussed the analysis of parallel fillet weld. In that case, we have discussed two cases. One, symmetrically loaded parallel fillet weld, and second one is unsymmetrically loaded parallel fillet weld. Now we will discuss the analysis of transverse fillet weld. Okay. So student, now we will discuss this question. What this question is saying, a welded joint with 10 mm fillet size is shown in figure. So fillet size of this weld joint is 10 mm, that is length of the fillet is 10 mm. The width of the plates is 120 mm. So width of the plate is given and it is 120 mm. Now if the allowable shear stress for the weld material is 100 megapascal, means permissible shear stress of weld material is given, and permissible shear stress of weld material is 100 megapascal, means actual maximum shear stress in the weld material, either it should be equal to 100 or less than 100 megapascal. Now the effect of normal stress is neglected. Okay, like you here in this diagram you can see this force is perpendicular to weld length. It is the weld length, and force P is perpendicular to weld length, means here this weld is transverse fillet weld. And as I discussed, in transverse fillet weld both shear stress and normal stress will come into picture. So examiner is saying we have to neglect the effect of normal stress. Okay, but suppose examiner has not mentioned this line, and in question only permissible shear stress is given, means in that case also whether in question it is mentioned or not, we will neglect the effect of normal stress. Okay, now we have to find the magnitude of F. Now magnitude of F, how we will find the magnitude of F? This welded joint is subjected to force. Here you can see this force is 2F which is applying, and here two weld is coming into picture. This is weld 1 and this is weld 2. Size of both weld is 10 mm. Size is given, so we can find throat thickness of the weld, because during design throat thickness is important. So if you will find a throat thickness of this weld, it will be h upon root 2. H is 10 mm, so upon root 2. So throat of both weld will be 10 divided by root 2. After solving, it is coming 10 divided by root 2. It is coming 7.071 mm. Now to find the value of F, we need to find maximum shear stress which are inducing in the weld. Now to find the maximum shear stress which are inducing in the weld, we do not know what is the throat area of weld. For that we need to know the throat thickness of weld which is given. Now what is the length of this weld? Okay, so here length of weld is not given, but without knowing the length of the weld we cannot solve this problem, because here F is unknown. So to find the expression of maximum shear stress, in that maximum shear stress already one unknown F is coming. So to calculate that F, first we should know what is the throat area of weld. For that we need to know what is the length of this each weld. It is not given in the question. So when I have already explained to you, whenever length of the weld is not given, in that case we will take length of the weld equal to width of the plate. Means we are assuming that in entire width of the plate we are making this welded joint. Okay, in entire width of the plate we are making this welded joint. So here length of both weld, that is L1 is equal to L2 is equal to, I am representing this as L, will be equal to width of the plate which is 120 mm. Now I can find the maximum shear stress in this weld. Now here in this weld shear stress only due to force will come, and if stress only due to force is coming, that stress is known as primary stress. Now here weld length is perpendicular to the force, and whenever weld length is perpendicular to the force, that weld is transverse fillet weld. And in transverse fillet weld I have already explained, when we are doing designing or doing analysis, in that case formula to calculate maximum shear stress is total force divided by total throat area. It is not actual formula, but during analysis we will use this formula. Means whether the weld is parallel fillet weld or transverse fillet weld, if stress is coming due to force, during analysis we will take formula of maximum shear stress or primary shear stress. Primary shear stress means stress due to force equal to total force divided by total throat area, which is actual formula for parallel fillet weld, which is formula which we have assumed for analysis for transverse fillet weld. It is not actual for transverse fillet weld, but during analysis we will use only this formula. Means since we are doing designing, so what will be the formula of maximum primary shear stress in the weld, because it is coming due to force. The expression will be total force, and here you can see this total force is 2F divided by total throat area. Now length of weld 1 is L, and first I am writing the expression here of total throat area. It will be throat area of weld 1, which is throat area of weld 1, length of weld 1 is 120 into throat is 7.071, and throat area of weld 2 is also same, because length and throat of both weld is same. So total throat area will be twice of this mm square. So primary shear stress in the weld during analysis will be total force, which is 2F, divided by total throat area, which is 120 into 7.071 into 2. Okay, and since here stress only due to force is coming, this primary shear stress in the weld will be overall maximum shear stress. Okay, now this overall maximum shear stress should be less than equal to permissible shear stress of the weld material. Yes sir. Now overall expression of maximum shear stress is 2F divided by 120 into 7.071 into 2. It must be less than equal to permissible shear stress of the weld material, which is 100 Newton per mm square. So from this we will get the limiting value of F. To calculate limiting value, use equal sign, and it is coming 100 into 120 into 7.071 into 2 divided by 2. It is coming 84852 Newton. Actual F, either it should be equal to this or less than this. Okay. So limiting value is 84852 kilonewton. If you will convert this into kilonewton, it will come F is equal to 84.852 kilonewton. So limiting value of F is 84.8452 kilonewton. Okay. So correct option for this question is option B. Okay. So correct answer is option B. So student, now we'll discuss eccentric loaded weld joint. Okay, in this case we'll discuss two type. One is type 1 and another type 2. First we are discussing eccentric loaded weld joint of type 1. So it is eccentric loaded weld joint of type 1. In this type 1 you can see it is a plate A, suppose, and it is plate B, and both are overlapping plate like this, and they are connected to the weld. Okay, they are connected to the fillet weld. So it is eccentric loaded weld joint of type 1. Plate A and B are connected with fillet weld. Okay. Now load P is acting like this. Okay, means perpendicular to this plate B, you can see. Now what we will do to calculate, ultimately our objective is to design. For design we need to calculate stress in the weld, and most importantly maximum stress in the weld. Now to calculate stress in the weld, first what we will do, we will transfer this force in the combined centroid of the weld. We will transfer this weld, this force to the combined centroid of this weld. Now suppose combined centroid of this weld is this. Okay, this is the combined centroid of this weld. Okay, now we will transfer this force P to the combined centroid of this weld, and combined centroid of this weld is this point CW. Now to transfer this load P here, we need to see what is the perpendicular distance of load P from this combined centroid, that is CW. Now perpendicular distance of load P from combined centroid is E. This is also known as eccentricity. Now if you will transfer load P in the combined centroid, one direct force P will come in this direction. Yes sir. And one moment will come in about combined centroid P into E in clockwise direction, because effect of this force P in terms of movement about centroid will be in clockwise direction, and magnitude of movement will be force P and perpendicular distance from CW, which is E. So if you will transfer this load P and the combined centroid of the weld, a direct force P will come and a moment P into E will come. Okay. Now you can see in this case of type 1 at combined centroid, both direct force and moment is coming. Direct force is coming means primary stress will induce in the weld, that is 100% sure. But since after transferring this force P in the combined centroid, one moment is also coming, which is P into E, and due to that moment secondary stress will also come into picture, means due to this moment P into E, secondary stress will also induce in the weld. Whether it is tensile or shear, that is different thing that we will discuss. If this moment is torsional moment for the weld, due to this secondary shear stress or torsional shear stress will induce. If this moment is bending moment for the weld, then due to that bending moment stress or normal stress or secondary normal stress, you can see, will induce in the weld. That is different thing that I will discuss. But since moment is coming in the combined centroid of the weld, means it is 100% sure secondary stress will also induce in the weld. So first we will understand effect of force P in this weld. Due to that primary stress will induce in the weld, how we can calculate that primary stress. Then we will discuss effect of this moment P into E. Due to this moment P into E, secondary stress will induce in the weld, and how we can find the magnitude and direction of that secondary stress. Okay. After that I will discuss this case with respect to design point of view, means if any unknown is coming into picture, how we can find that unknown by ensuring this our welded joint is safe. But before that first we need to discuss due to force P which type of primary stress is coming and how we can calculate that, and due to moment P into E which type of stress is coming in the weld and how we can calculate that. Okay. So for that I am drawing the line diagram of this weld separately. So it is the line diagram of weld. Suppose this weld is weld 1 and this weld is weld 2, and it is the line diagram of this weld, and it is the combined centroid of the weld. Now in combined centroid, one direct force P is coming like this, and one moment P into E is coming like this. Okay. Now first we will understand the effect of force P. First we will understand the effect of force P. So first I am explaining the effect of force P, and that I have already explained. Due to force P, since it is direct force, primary stress will induce in the weld. Now we will say primary stress, that we understood, but it will be shear or normal. So whenever question is coming from eccentric loading, we will always consider that due to force P, primary shear stress is inducing in the weld. It will not matter whether it is this force P is coming in the parallel to the length of the weld, or force P is coming perpendicular to the length of the weld. Whenever direct force P is coming in the eccentric loading case, we will always assume during design, due to force P, primary shear stress is inducing in the weld. Okay, and that to calculate primary shear stress, the area which we will consider is throat area. Okay, one point you can always keep in your mind during eccentric loading or any type of case during design of welded joint, the important cross section or important area is throat area. Important thickness of the weld is throat thickness, because that thickness is minimum, means that thickness is critical. So in eccentric loading case, we will always calculate stress in throat of the weld. Okay, so whenever I am calculating stress, whether it is primary or secondary, I will, in eccentric loading case, I will always calculate stress in the throat. This is one most of the important point. Second point, whenever you are calculating stress due to direct force, that is primary stress, we will whether force is parallel to the weld length or perpendicular to the weld length, in eccentric loading we will always consider that where in weld primary shear stress is coming, means we will neglect the effect of normal due to force P. Okay, and the formula to calculate primary shear stress will always be total force divided by total throat area, means this will be same in H point of the throat. Okay, so due to force P, whether this force P is parallel to weld length, perpendicular, it will not matter. Due to this force P, primary shear stress will induce in the weld. Primary shear stress will induce in the weld. I am denoting this primary shear stress as tau dash. As tau dash. I will use for primary stress dash suffix and for secondary double dash. Okay, and since it is shear, I am using letter tau. Okay, so primary shear stress in the weld. Now, the formula to calculate primary shear stress in the throat is primary shear stress at each point of the thread will be same, and formula to calculate that primary shear stress is total force due to which primary shear stress is coming divided by total throat area. Here it is nothing but throat area of this weld. It is, I am writing here, throat area of total weld, of total throat area. Okay, like suppose suppose length of weld 1 is L, and right now this diagram is symmetric, so length of weld 2 is also L, and suppose T is throat. So in this case, what will be the expression of total throat area? That you can calculate in numerical. Like throat area of weld 1 will be LT, throat area of weld 2 will be LT. So total throat area for this case is 2LT. It is for this case, but for different case it can come different. Okay, important is due to force P in eccentric loading, always primary shear stress will induce, which will be same at each point of the throat. Okay, and formula to calculate that primary shear stress is total force P divided by total throat area. Okay, it is the magnitude. Now next point is how we will find direction of this primary shear stress, because here direction is also important, because when we will do design, this direction will play very key role or important role during design. So direction of primary shear stress will be opposite to force P. So now I am talking about direction. It will be opposite to force P. I am not going on derivation. I am just explaining the steps. Okay. So primary shear stress will be same at each point of the throat, whose formula is total force P divided by total throat area. It will be same at each point of the throat. And how to find its direction? It will be opposite to P. Right now, suppose I am drawing the primary shear stress of this point A. To explain this, how to calculate primary and secondary shear stress, secondary stress due to secondary stress due to this movement, I will draw the direction at point O to explain. You can draw at any point. Right now, to explain the concept, I am drawing at point A. Okay. Now, what will be the direction of primary shear stress at point A? I am drawing only for point A. You can draw for any 2 point. I already explained primary shear stress will be opposite to force P. Right now force P is coming in downward direction. Right now force P is coming in downward direction. So definitely primary shear stress of point A will be in upward direction. I am denoting this as tau A dash. Dash for primary shear and A for, I am talking about primary shear stress of point A. Okay, it is different thing. Primary shear stress of each point will be remain same and direction will be opposite to P. But since right now I have drawn primary shear for point A, I have used the suffix point A. Okay, so it is the primary shear stress. Now second important point, what will be the effect of moment P into E? It is important. Okay, so second we are discussing how to find the effect of moment P into E. Okay, now the effect of moment P into E. Okay, now this P into E, due to this secondary stress will come, that is 100% true, but it will be secondary shear, or you can also say torsion shear, or secondary normal, or you can also say bending stress. So for that we need to see this moment P into E is bending moment for this weld, because we are calculating stress in weld, or torsion moment of this weld. So if any moment is coming in the axis which is along the plane of weld, that moment will be bending moment for the weld. But if any moment is coming about the axis which is perpendicular to the plane of weld, that moment will be torsion moment of the torsion moment for the weld. Okay, you already know the definition of torsion moment and bending moment, you have studied in strength of material. If resistance due to resistance of moment is about perpendicular axis of the cross section in which we are calculating stress, that resistance of moment will be torsion moment, due to which torsion shear stress will induce. If resistance of moment is about along axis of the cross section in which we are calculating stress, then that moment will be bending moment for the cross section, and due to that moment bending stress will induce in the cross section. Same will be applied here. Here we are calculating stress in the weld, and we always calculate stress in the weld along plane, along plane which is along length, in the plane which is along length. So it is the plane of weld. The plane which is along length is known as plane of weld. So it is the plane of weld. Now if any moment is coming about the axis which is along axis for plane of weld, that moment will be bending moment. If any moment is coming about the axis which is perpendicular axis for the plane of weld, then that moment will be torsional moment. So here you can see, suppose the axis which is coming along the plane of weld, I am denoting those axes as x axis and y axis. So it is x axis, it is y axis. If you want to draw, you can draw. It is x axis, it is y axis, and the axis which is perpendicular to the plane of weld, this axis, it is z axis. Okay, so if moment is coming about x axis and y axis, then that moment will be bending moment for this weld. If moment is coming about z axis, that moment will be torsion moment for the weld. And here you can see this moment P into E is coming about z axis, means about the axis which is perpendicular for this plane of weld, means this moment P into E is nothing but torsional moment for this weld. I am writing in short T dot M dot. It is torsion moment for this weld, and since it is torsion moment for this weld, due to this moment secondary shear stress or torsional shear stress will induce in the weld. Means here this moment P into E is acting like torsion moment for the weld, and due to this secondary or torsional shear stress will induce in the weld, and this shear stress I will denote as tau double dash. Okay, double dash for secondary shear. Okay, so due to this torsion moment, secondary shear stress will induce in the weld. Now what is the formula to calculate torsion shear stress? That we already studied in strength of material. Formula to calculate torsion shear stress or secondary shear stress is T upon J into small r, where T is torsion moment, J is polar moment of inertia about centroid, and R is radial distance of the point in which we are calculating torsion shear stress from centroid. So if you will calculate a torsion shear stress at any point, the formula to calculate torsion shear stress, that is T double dash, is T, which is torsion moment. In this case, this torsion moment is P into E. So suppose I am representing this torsion moment P into E as T. Okay, divide by J, where J is polar moment of inertia of all the weld about combined centroid. So can I say J is nothing but, I am writing the J, J is polar moment of inertia or area moment of inertia of weld about combined centroid. When I am use polar moment of inertia, means that is the area moment of inertia about the axis which is perpendicular to the plane of weld. Means this is polar moment of inertia about Z axis which is passing through combined centroid. Okay. So J is polar moment of inertia of weld about combined centroid. That you can calculate. It is this thing you have already studied in engineering axis, but I will explain in this case how to calculate J for this case. Okay. And into small r dash, or you can also say small r. Small r is radial distance of the point. Small r dash is radial distance of point at which we are calculating secondary shear stress, that is tau double dash, from combined centroid which is CW. Okay, if you are calculating stress at this location, you need to find this distance. If you are calculating stress at point A, you need to find this distance. Means small r is radial distance of point at which we are calculating secondary shear stress from combined centroid of the weld. So it is the formula, and it will change with r. If r is more, the magnitude of secondary shear stress will be more. If r is less, magnitude of secondary shear stress will be less. It will depend upon this distance r dash. So it is the magnitude of secondary shear stress. Now to use this formula, T is very easy. R dash is also easy. If you are finding stress at point A, find the distance of point A from combined centroid. But here, to use this formula, first we need to calculate J, that is polar moment of inertia of the weld. Now how to calculate polar moment of inertia? So for how we will calculate, suppose I want to calculate polar moment of inertia of this weld which is in this diagram. So for that, what you can do, just for understanding I am explaining this. You can calculate first polar moment of inertia of weld 1 about combined centroid. Similarly, polar moment of inertia of weld 2 about combined centroid. Okay. Now, while calculating polar moment of inertia of weld 1, we will consider weld 1 as rectangle, whose one dimension is length, and in whose one dimension, that is height, you can say, will be thickness. And here thickness, which thickness you will take? Throat thickness, because in weld we are always consider calculate stress at throat. So whatever thickness you will take, that thickness should be throat thickness. So how to calculate? First I am calculating polar moment of inertia of weld 1 about centroid of weld 1. Now weld 1, the centroid of weld 1 will be at midpoint of this weld 1, which will be at this location right now. Okay, don't be in hurry. First you need to locate combined centroid of weld, which is CW. Right now this diagram is symmetric about x-axis. First you need to understand how to locate combined centroid of this weld, because you need to transfer this force P at CW. How to locate? First see, is this diagram is symmetric about x-axis? Yes sir. So it will be centroidal x-axis of this weld. Is this diagram is symmetric about y-axis? So in mid-axis will be centroidal y-axis of this weld, because it is symmetric about y-axis. Now intersection of these two axes is combined centroid of this weld. In this way you can locate combined centroid if diagram is symmetric. Okay. Now after that, how to calculate polar moment inertia? For that, first locate the centroid of weld 1 and centroid of weld 2 individually, because to calculate polar moment inertia about combined centroid, that is CW, we will use parallax theorem. For that, first you need to locate the centroid of weld 1 just to calculate polar moment of inertia. So centroid of weld 1 is C1. Okay, and since weld 1 is symmetric, it will be in midway of this weld 1, and centroid of weld 2 is suppose C2. Okay. Now how to calculate? First I am calculating polar moment inertia of weld 1 about combined centroid. For that we will use parallax theorem. First we will calculate polar moment inertia of weld 1 about the centroid of weld 1. First we will calculate polar moment inertia of weld 1 about the centroid of weld 1, which is C1. So it is about the centroid of weld 1. Now calculate polar moment inertia of weld 1 about CW. CW is the combined centroid, but it is not the centroid of weld 1. Centroid of weld 1 is C1. So it is polar moment of inertia about centroid of weld 1. Now to calculate polar moment inertia about CW, we will use parallax theorem. What is parallax theorem? In the polar moment inertia which is about the centroid of weld 1, in this add a term plus add term, and what term we need to add? A A is AT1, I can say AT1 is throat area of weld 1 or area of weld 1 into R square and what is here? R is distance between, radial distance between C1 and CW. What is R? It is what is R here? Radial distance between C1, that is centroid of weld 1, and CW. Okay, like in this case, how to calculate polar moment inertia of weld 1 about centroid of weld 1? Now, for any rectangle, formula to calculate polar moment inertia is I about centroidal x-axis plus I about centroidal y-axis. If you add both this, we'll get polar moment inertia about centroid. Okay, and I about centroidal x-axis for rectangle is bh³ by 12, and I about centroidal y-axis is hb³ by 12. And if we will add both, we will get total polar moment of inertia about centroid. Now here you can see with matlab the dimension which is parallel to x-axis, that dimension for weld 1 is L. H matlab the dimension, H means the dimension which is perpendicular to the x-axis, or you can say parallel to the y-axis, and here that dimension is throat thickness T. So if you will apply bh³ by 12, it will be LT³ by 12 plus h³ by 12 means TL³ by 12. So it is polar moment of inertia of weld 1 about C1 plus, now we will use Parakram's theorem, plus area of weld 1. Area of weld 1 is LT into R square. R is distance between centroid of weld 1, that is C1, and combined centroid, that is CW. Okay, right, that distance you can calculate. Suppose right now I am considering this distance as R1, so it will be R1 square. Okay, in numerical you can calculate this distance. So it is the combined polar moment inertia of weld 1 about combined centroid. In a similar manner, we can also calculate J2CW. In similar manner, you can also calculate J2CW. Yes, sir. In same manner. Right now, since this diagram is symmetric, you can say J1CW and J2CW will come same because this diagram is symmetric. So can I say due to symmetricity, J1CW will come exactly equal to J2CW? How? Polar moment inertia of this weld 2 about its centroid will be LT³ by 12 plus TL³ by 12, same expression, plus area of throat LT into distance between C2 and CW. And due to symmetric, if this distance is R1, suppose I am denoting this distance as R2, so R2 will also come equal to R1. So right now, due to symmetricity, J2CW will come same as J1CW. And after calculating polar moment inertia of all weld about CW, you will add all this term, you will get total polar moment inertia, that is expression of J, and it will be J1CW plus J2CW. So in this manner we can calculate, I am writing in different space. So in this manner we can calculate polar moment inertia of whole weld about combined centroid. Okay. Sometime exam might give this value directly. Okay, but if you are doing designing means suppose throat is unknown. If throat is unknown, you can calculate exact value of this. But if throat is unknown and our objective is to find throat, in that case we will neglect this T³ term. Okay, we will not always neglect. When our objective is to calculate throat, means throat is unknown. In that case, we will neglect T³ term because throat will be less than less as compared to length of weld. Yes, sir. And throat of cube will be very less as compared to length. So we can say this term will be negligible as compared to this term. So we can neglect this term if throat our objective is to calculate throat. In that case, we will neglect T³ term. So it is the method to calculate combined polar moment inertia of whole weld about CW. Okay, and this is the J in this case. Now, how to find direction of this secondary shear stress? Now, to find direction of secondary shear stress, how to find? I am explaining directly in diagram. Suppose I want to find the direction of secondary shear stress at point A. Secondary shear stress at point A will be T upon J into RA. T is torsional moment, J is polar moment inertia. It will remain same. But R will change, R dash will change with point. So RA, I am calculating secondary shear stress at point A, means we need to calculate distance of point A from combined centroid. Okay, in this diagram, it is the distance of point A from combined centroid, this distance. Okay, in this diagram, these distances are A. Now, it is the magnitude of secondary shear stress at point A. Now, what will be its direction? To find the direction of secondary shear stress, first draw a line which is perpendicular to the line, a line of point join, first draw a line which is perpendicular to the line joining point A and CW. Okay. So first draw a line which is perpendicular to the line joining point A and CW. Means direction of secondary shear stress will be, I will explain how to find sense. First draw the direction will be perpendicular to this line, means line joining point A and CW. Right now this is the line joining point A and CW. So direction of secondary shear stress will be perpendicular to this line, means this angle will be 90. Now in this direction secondary shear stress will come. But what will be the sense? So to decide sense, first see what is the direction of movement due to which secondary shear stress is coming. It is coming due to this movement which is in clockwise direction. Now when I was discussing the direction of primary shear stress which was coming due to force P, I had taken opposite direction, means force P was downward, I had taken this as upward. In same manner, the direction of movement about centroid is clockwise, and stress due to this, the stress which is coming due to this movement is secondary shear stress. So directions of secondary shear stress will be such that its effect about centroid should be opposite to this movement. Movement is clockwise. So in this line will take sense such that its effect about combined centroid should be anti-clockwise, means opposite to movement due to which this secondary shear stress is coming. So now in this line, if I want to apply a sense or arrow which effect about centroid should be CW should be anti-clockwise, for that we need to rotate this line is like this point like this, and for that we need to take arrow in this direction. So in this case it is the direction of secondary shear stress. Means how to decide sense? To decide sense, we need to take sense such that its effect about centroid should be opposite to the movement. Okay, effect about CW should be opposite to movement in terms of direction. Okay, in similar manner you can draw the direction of any point of secondary shear stress, and you can find the value of any point of secondary shear stress of this weld by using this formula. Now here you can see both primary and secondary shear stress is shear, and since nature of both stress is same, both are shear and coming at same point, so due to this primary and secondary shear, resultant shear will induce in point A, because both are shear. So due to this, resultant shear stress will induce. Now how to find that resultant shear stress? For that you can find the vector angle between primary shear stress and secondary shear stress. Right now suppose at point A, vector angle between primary shear stress and secondary shear stress is this theta angle. Okay, which angle is known as vector angle? First draw both vectors such that tail end of both the vector is coinciding. Here you can see tail end of both vector is coinciding. Okay, and arrow should be in outward direction, means vector arrow should be, means head should be in outer direction. Okay, draw like this. Okay, don't draw like this. This is also correct. This is also correct. This direction of secondary shear stress is also correct. But in this diagram, the tail of both vector is not coinciding each other. To find vector angle, first draw both vectors such that tail of both vector is coinciding and arrow of the vector is going in outer direction. In that case, the smaller angle between primary and secondary is known as vector angle. Smaller angle means there will be two angles. One angle is this, one angle will be this. This is a smaller angle. This angle is known as vector angle. Okay, vector angle means angle which is less than 180 degree. That will be smaller angle, because you can see this angle is greater than 180. It is less than 180. So that smaller angle is known as vector angle. And if you have calculated vector angle between primary and secondary, how you can calculate resultant shear stress at any point? That I am explaining for point A. You can calculate this for any point. For that, first draw primary shear stress, then draw secondary shear stress, and tail end of both the vectors should meet with each other, and arrow should be in outer direction. Then find the smaller angle between these two vectors, which is known as vector angle. I am denoting that angle as theta f for point A. So then resultant shear stress at point A will be, tau A is resultant shear stress. Resultant shear stress at point A, and its formula is tau A dash square. Both are shear, that's why I am applying this formula, plus tau A dash double square plus, in all term plus is coming, 2 tau A dash dash double dash cos theta A. If you want, you can remember this formula. Okay, this is important formula. So it is resultant shear stress at point A. Okay. Okay. Similarly, if you want to calculate, suppose this is point B, resultant shear stress at point B, resultant shear stress at point B. In examiner can ask at any point. First find primary shear stress. Primary shear stress will be same at each point, and its formula will be P divided by throat area. So it is also the primary shear stress at point B. Direction will be opposite to P is downward, so it will be upward. Now secondary shear stress at point B, formula will be T upon J into RB. RB is distance of point B from center CW. Okay, so that will be secondary shear stress at point B. Direction, join this point B. I am not drawing, I am just explaining, with CW, and draw a line which is perpendicular to this line. Now in that line, takes sense such that its effect about centroid should be opposite to movement, that is anti-clockwise direction. After that, find vector angle between primary and secondary. Then through this formula you can find resultant shear stress. Okay, so in this way we can find primary and secondary shear stress of any point. Now next point is, if question is coming for design, then we need to find this resultant shear stress. First, for that, first we need to find primary, then secondary, then a vector angle, then we can find resultant shear stress. But for design, we'll find resultant shear stress for critical point. Critical point is that point whose chances of failure is maximum. Okay, so if we will keep safe critical point, means entire weld will be safe. So whenever we are doing the designing, we'll find this primary, secondary, or resultant shear stress at critical point. So with design point of view, first now we need to understand how to find critical point. Okay, and if you will understand how to find critical point, then calculate the resultant shear stress of critical point. So for design point of view, we need to find this resultant shear stress at critical point. So here I will explain how to find critical point first. Then calculate resultant shear stress at the critical point, that is different thing. Okay, so for that again I have taken same diagram. Here one force P was coming and one moment in this direction P into E was coming. Now right now I am explaining how to find critical point. Okay, or whenever you are doing designing, first find critical point, then find resultant shear stress at the critical point. Now which point will be critical? At which resultant shear stress will be maximum. Okay, okay, which point chances of failure of which point will be maximum, at which stress is maximum. And here primary and secondary stress you don't have to see, you have to see combined effect of primary and secondary, that is resultant shear stress. And the point at which resultant shear stress is maximum, that point will be critical point. So the point at which resultant shear stress is maximum, that point will be critical point. Okay, now this resultant shear stress will depend upon magnitude of primary shear stress, magnitude of secondary shear stress, and vector angle between primary shear and secondary shear. Okay, so resultant shear stress will depend upon primary, secondary, and vector angle between primary, secondary. If primary and secondary is more, stress is more, means definitely their resultant will also come more. Now for same value of primary and secondary shear stress, if vector angle is less, then resultant will be more. You can easily imagine, if in this diagram vector angle is 0, in this diagram vector angle is 180, here both vector will get add, here both vector will subtract, means here value will come more for same value of primary and secondary. Means what I am trying to say, if vector angle is less for same value of primary and secondary, then resultant will be maximum. Now so where resultant will be maximum, where primary is maximum, secondary is maximum, and vector angle is minimum. Vector angle is minimum. Now primary shear stress in each point is same. So critical while deciding the critical point, we need not to see where primary shear stress is maximum, because primary shear stress is maximum at all points. But secondary shear stress value will change with R, and the point for which R is maximum or R dash is maximum, that point at that point secondary shear stress will be maximum. So can I say, to find critical point, First we need to see where secondary shear stress is maximum, and it will be maximum where R dash is maximum. So we need to see where R dash is maximum. Okay. Now, but resultant shear will not only depend upon magnitude of secondary, it will also depend upon vector angle. So apart from that, we need to also see where vector angle is minimum. Okay, because if vector angle is less, then resultant will be more. And the point at which secondary is maximum, that is R dash is maximum. And the point at which vector angle, that is theta, is minimum, that point will be overall critical point. Can I say? Yes, sir. But for that, first what you need to do, for finding critical point in weld component, in this case, first what you need to do, draw the primary and direction of primary and secondary shear stress. Right now you need not to calculate value, first only draw the direction, and draw the direction of primary and secondary shear stress in some selected point. And these selected points are the points which are farthest from points from centroid CW in all directions. Like in this side, farthest point from CW is this point, which I am denoting as A. In this side, farthest point is this, which is B. In this side, farthest point is C, which is C. In this side, farthest point is D, this point, which I am denoting as D. Now calculate, draw the direction of primary shear stress and secondary shear stress in this point. Now the direction of primary shear stress will be opposite to P. Right now P is downward, so it will be upward. So this is primary shear stress at point A, point B, it is point C, and point D. I am denoting this as tau A dash, I am denoting this as tau B dash, I am denoting this as tau C dash, I am denoting this as tau D dash. So it is the direction of primary shear stress. Now draw the direction of secondary shear stress for these points. So first I am drawing the direction of secondary shear stress for point A. For that, join point A with CW. Now draw the line which is perpendicular to this line. It will be in this direction. Now draw the line which is perpendicular to this direction. It will be in this direction. Now in this line, take arrow such that its facts about centroid should be anti-clockwise because movement is clockwise. So for that we need to take arrow in this direction. So it is tau A double dash, and it is the vector angle between primary and secondary, that is theta. Okay. Similarly, draw the secondary shear stress for point B, point C, point D. Now to draw the secondary shear stress of point B, we need to draw a line which is perpendicular to this line, and the line which is perpendicular to this line will be in this direction, means this angle is 90. Okay. Now in this line, take arrow such that its effect about centroid should be anti-clockwise. For that we need to take arrow in this direction. So it is secondary shear stress of point B. Now angle between vector angle between primary and secondary in this location is this. Okay. To locate this angle, first ensure that tail and both the vector is coinciding with each other, and vector in arrow is in outward direction. Then smaller angle between these two vector is vector angle. Now you can see here theta A is less than 90 and theta B is more than 90. Okay. Now similarly, draw the secondary shear stress for point C. It will be perpendicular to this line, which will be in this direction. Now in this line, take arrow or sense such that its effect about CW should be anti-clockwise. It will be in this direction, and this is vector angle theta C. Now we are drawing secondary shear stress of point D. It will be in this direction. Okay. Now in this line, take arrow such that its effect about CW should be anti-clockwise, and it is the vector angle theta D, and it is tau D double dash, it is tau C double dash. Now the which point will be critical? For that, see two things. The point for critical point, we need to see two things. Where secondary shear stress is more, for that you need to do distance R dash, and where vector angle is less, that is minimum. For that you need to see vector angle theta. So to find critical point, first see where tau double dash is more, and tau double dash will be more where distance R dash is more. So first see in these 4 points where R dash is more. First see in this point where R dash is 4. Means in terms of R, which points can be critical. So here with symmetricity, the distance of point A from CW is RA, this distance is RB, this distance is RC, and this distance is RD. In numerical you can calculate this distance. But with symmetricity, can I say here RA will be equal to RB, will be equal to RC, will be equal to RT? Through observation you can say RA, RB, RC, RD are same because this diagram is symmetric. And since RA, RB, RC, RD are same, so can I say in this case R is maximum for all these 4 points? Means can I say in terms of R, these all 4 points are equally critical? because we need to see where R is maximum, and R is maximum in all these 4 points because value of R in these 4 points are same. So in terms of R, for this case, critical points can be A or B or C or D, but it is in terms of R, and in terms of R, A or B or C or D are equally critical because value of R is same for all these 4 points, and R maximum, and this value is maximum. Okay, because if you will take any other points apart from this 4 point, value of R is less than this, will be less than this. Okay, but means in these 4 points R is maximum, so these 4 points will be equally critical in terms of R. But to see critical point, we need to see one more thing, where vector angle theta is less, because when vector angle is less, then resultant will be more. So you need to see. Now here you can see vector angle theta between at point A, that is theta, at point D is theta D, both are less than 90 degree. And with symmetricity you can see value of theta A, theta D will come same, which is less than value of theta A, theta D will come same, which is less than 90 degree. In numerical you can calculate value. And how in same, suppose this angle is alpha, this angle is alpha, just for understanding. Now if angle between two line is alpha, angle between their smaller angle between their perpendicular line will also be alpha. So line which is perpendicular to this line is this, and line which is perpendicular to horizontal is this. So if this angle is alpha, the angle between the smaller angle between their perpendicular line will also be alpha, and perpendicular line of this line is this, and perpendicular line of horizontal is this, means this angle will also be equal to alpha. Similarly, if you will calculate this angle with symmetricity, this angle will also come alpha, and when it is alpha, theta D will also come alpha. Means here you can see theta A and theta D is same. In numerical you can calculate exact value, and which is less than 90. Now if you will, with symmetricity you will say theta B and theta C is also same, but it is greater than 90 degree, and you have to see less value of theta. So here if theta is more, means you need not to see this value, you need not to calculate this value, because we have to focus on less value of theta. And can I say in this case theta is minimum at point A and D? Okay, and A and B coming in simultaneously, because at both point A and D theta is same and is minimum. So can I say in terms of theta, either point A or point D will be critical? Now next question is, which point will be overall critical? That point will be overall critical where R is also maximum and theta is also minimum. Means can I say common points between this and this will be overall critical point, and here common between points between this and this are A or D, because for point A or D, R is also maximum and theta is also minimum. So can I say in this case overall critical point points are either A or D. Out of A and D you can take any point as critical, because for both A or D R is maximum, and for both A or D theta is minimum. So if you are designing, you can take A as critical point. For designing you can refer D as critical point, because here A or D both are equally critical. So overall critical point in this component is, welded component is A or D. So when you are doing designing, either you will calculate resultant shear stress at point A and point D, and that resultant shear stress will be maximum shear stress, because they say that, because that shear stress is shear stress of the critical point. Okay, so during design we will calculate resultant shear stress of critical point, and for that find primary shear stress at critical point, that I have already explained. Secondary shear stress, how to calculate X, I have already explained. Then draw direction, then find vector angle, and then find resultant. And resultant shear stress of critical point will be overall maximum shear stress. So resultant shear stress of critical point is nothing but, can I say, it will be overall maximum shear stress. Now during design, this overall maximum shear stress should be less than equal to permissible shear stress of the welded material. In question, permissible shear stress can be directly given. If it is not directly given, examiner will give shear strength. I am saying shear strength. So permissible shear stress will be shear strength upon Fs. If examiner is giving tensile strength, then definitely examiner will mention which theory of failure need to be used. If it is theory of failure is not given, then definitely either examiner will give permissible shear stress value or shear strength. If shear strength is given, then permissible shear stress will be shear strength upon Fs. And overall maximum shear stress of the critical point must be less than permissible shear stress. Okay. So it is the eccentric loaded weld joint of case type 1. Now I will solve one question related with this case. Okay. So student, now we'll discuss one question. What this question is saying, this two plate, suppose this is plate A and plate B, are connected by welded joint. Now if permissible shear stress of weld material is 100 megapascal, so permissible shear stress of weld material is given, it is 100 megapascal, tau p is given 100 megapascal or Newton per m square, means actual overall maximum shear stress either should be equal to 100 or less than 100. Now examiner asking recommended size of the weld, means leg we have to find. So if we will find throat of the weld, then we can find leg of the weld also. Okay, it is the eccentric loaded welded joint. Suppose I am denoting this force as P, it is 10 kilonewton, in Newton it will be 10,000 Newton. Now we will transfer this force P in the combined centroid of this weld. Suppose this is the combined centroid of this weld. So first we will locate the location of combined centroid of the weld. For that I am drawing this diagram separately. And to draw this weld diagram separately, I will draw line diagram. Line diagram means, if you will draw line diagram of these welds, it will be like this. Suppose top weld I am saying weld 1, so it is weld 1. Now it is weld 2. Length of both weld is 100 mm. Here all dimension are in mm, I am not writing the unit. This distance is 150 mm, it is given in the question. Now I want to locate the combined centroid of this weld. Now how to locate? So to locate combined centroid of this weld, first we will see whether this diagram is symmetric about x-axis. Yes sir, it is symmetric about x-axis. Okay, because if you will draw this x-axis in between this diagram, in middle of this diagram, the diagram which is above this axis and the diagram of weld which is below this axis are exactly same. So it is symmetric about x-axis. So symmetric x-axis in this case will be centroidal x-axis. So this whole distance is 150. So definitely this distance will be half of 150, that is 75 mm. Similarly, this diagram is also symmetric about y-axis. So here symmetric y-axis will be centroidal y-axis. This symmetric y-axis is nothing but centroidal y-axis. This whole distance is 150. So this whole distance is 100. So this distance will be 50. Okay, now the intersection of the centroidal x-axis and y-axis is the location of combined centroid of this weld, which I am denoting as CW. So it is the location of combined centroid. Okay, and this distance is 50. If you see here, this distance is 50, can I say? Okay. Now to transfer this load P at the combined centroid, we need to see perpendicular distance of this force P from combined centroid, which I am denoting as E. So perpendicular distance of this load P from combined centroid is this distance, which is E. Okay, and this is 200, this is 50. So definitely value of E is 250 mm. And if you will transfer this load P at combined centroid, it will be like this. One downward force will come at combined centroid, which is P, and one movement will come in clockwise direction, which is P into E. So here one downward force will come in this direction, which is P, and when movement will come in clockwise direction, which is P into. Okay, so this is P, direct force P is coming and moment P into E is coming. Now due to force P, primary shear stress will come, and due to moment P into E, secondary shear stress will come. Now to calculate primary shear stress, first we need to calculate area of throat. To calculate secondary shear stress, we need to calculate polar moment of inertia of this entire weld about combined centroid. Because formula to calculate secondary shear stress due to this moment, because this moment is torsion moment for this component, and formula to calculate torsion shear stress is T upon J into small r dash. For that we need to first we need to calculate polar moment of inertia of those weld. So by drawing this diagram separately, first I am calculating area of the throat and polar moment of inertia of this combined centroid. And if we will calculate area of the throat and polar moment of inertia of this weld about combined centroid, it will be area of throat. Area of throat is 3. Throat area for weld 1. Suppose I am denoting throat thickness as T. So throat area of weld 1 will be 100 T, because length is 100. Throat area of weld 2 will also be 100 T. So total throat area will be 200 T mm square. Now we will calculate polar moment of inertia of this weld about combined centroid. So for that, suppose this is weld 1. First we will calculate polar moment of inertia of weld 1 about combined centroid. For that we need to calculate polar moment of inertia of weld 1 about its centroid. So for that I need to locate centroid of weld 1. Now centroid of weld 1 will be in middle of this line, which is this. So it is centroid of weld 1. Similarly, this is the centroid of weld 2. So first I am calculating polar moment of inertia of weld 1 about combined centroid. For that, first I will calculate polar moment of inertia of weld 1 about its centroid, that is C1. Now polar moment of inertia of weld 1 about C1 will be BH cube by 12 plus HB cube by 12. Here B is 100 and H is T. So it will be 100 into T cube by 12 plus T into 100 cube by 12. It is polar moment of inertia of weld 1 about C1. Now to calculate polar moment of inertia of weld 1 about CW, we need to apply Parakram's theorem. For that we will add a term, area of the weld, and throat area of weld 1 is 100 T into R square, where R is distance between C1 and CW. And here you can see distance between C1 and CW is equal to 75 mm. So it will be 75 square. So it is polar moment of inertia of weld 1 about combined centroid, that is CW. And since here throat is unknown, so to calculate throat during design we will neglect this term. So I am neglecting this term. And if you will neglect this term, value of J1 will come 100 cube divided by 12 plus 100 into 75 square. You can check calculation. It is coming 645833.33 T mm to the power 4. You can check calculation, it is your part. Yes, 6A45833.33 T. Now if we will calculate polar moment inertia of weld 2 about combined centroid, it will come exactly equal to this. Why, sir? Because this diagram is symmetric. So J2CW will also be same. So if we will calculate total polar moment inertia about combined centroid, we need to add J1CW plus J2CW, and both are same. So if you will calculate this, it will come 1291,666.667 T mm to the power 4. So it is the combined centroid of weld, polar moment of weld about combined centroid. So now we can calculate stresses in this case. Primary shear stress, for that we need to know area of throat, we have calculated. We can calculate secondary shear stress because we have calculated polar moment inertia. But here we will calculate primary shear stress, secondary shear stress, then resultant shear stress at critical point. So here first we need to find or locate the critical point. Now how we will find critical point? So it is the location of combined centroid. Now what we will do to find critical point? First see all the points which are farthest from this CW in all sides. In this side the farthest point is this point, suppose I am denoting this point as A. In this side farthest point is this point, suppose I am denoting this point as B. In this side farthest point is this point, I am denoting this point as C. And in this side farthest point is this point, suppose I am denoting this point as D. Now we will draw the primary and secondary shear stress in these points. First I am drawing primary shear stress. So primary shear stress, how to draw primary shear stress? The primary shear stress in each point will be opposite to the direction of force P. Right now P is downward, so primary stress at point A will be this. Suppose this is tau A dash. Primary shear stress of point B will be in this direction. Suppose this is tau B dash. Primary shear stress of point C will be in this direction. It is tau C dash. Primary shear stress of point D will be tau D dash, which will be opposite to P, that is in this direction. Now we will draw secondary shear stress. To draw secondary shear stress, first we will join point A with combined centroid. I am drawing secondary shear stress of point A. Now we will draw a line which is perpendicular to this line, and the line which is perpendicular to this line will be in this direction. Now in this line we will take arrow such that its effect about combined centroid should be opposite to movement. Movement is clockwise, so its effect about combined centroid should be anti-clockwise direction. So secondary shear stress of point A will be in this direction. Okay, and vector angle between tau A dash and tau A double dash is this theta. Similarly, if you will draw secondary shear stress of point B, it will be in this direction. Tau B. You can, by same method you can draw this. If you draw secondary shear stress of point C, join point C by CW. Now draw its perpendicular, and in this line take arrow such that its effect about combined centroid should be anti-clockwise, and it will come in this direction. Similarly, if you will draw the secondary shear stress of point D, it will be in this direction with this arrow. Okay. Now it is the vector angle between primary and secondary, that is theta D at point D. It is vector angle at point B, and it is vector angle at point C. Now to find or identify critical point, we need to see for which point distance R is maximum and for which point vector angle theta is minimum. Distance of point A from combined centroid. Suppose this distance I am representing as RA. You can calculate this distance. It is simple mathematics. Here this distance is 75. You can check. Here this distance is 50 and this angle is 90. So RA will be root over 75 square plus 50 square. So if we'll calculate distance RA, it will come root over 75 square plus 50 square. And after calculation it is coming root over 75 square plus 50 square. After calculation it is coming 90.139 mm. You can check calculation. And with symmetricity you can check RA will be equal to RB, that is will be equal to RC, that will be equal to RD. Okay. So this is distance R. Now vector angle, that is theta, it is less than 90 degree. So, but how much its value will be? So for that first calculate this angle. Suppose I am denoting this angle as alpha. And in this triangle, if you will apply tan alpha will be perpendicular upon base. In this triangle, if this is alpha, perpendicular is 75 and base is 50. So it will be 75 divided by 50. And from this, if you will calculate value of alpha, it is coming tan inverse 75 divided by 50. It is coming 56.31 degree. You can check calculation. Now if angle between smaller angle between two line is theta, then a smaller angle between their perpendicular line will also be theta. So here angle between this line and horizontal is alpha. So angle between their perpendicular to this line is this, perpendicular to this line is this. So angle between their perpendicular line, that is theta A, will also be equal to alpha. So can I say here theta A is equal to alpha, which is 56.31 degree. With symmetricity, if you calculate theta D, it will also come exactly equal to theta A. Okay. Now what about theta B, theta C? You need not to calculate value of theta B, theta C, because they are greater than 90 degree. And to find critical point, we need to see where theta is less. So if it is greater than 90, definitely it will be more than this. So definitely this value will be lesser than this. Okay. So we need not to calculate magnitude of theta B and theta C. It is theta C. Now critical point. The critical point will be the point where first distance R is maximum or R dash is maximum, and second where vector angle theta is minimum. So here you can say distance R is maximum in all A, B or C or D point. Means with respect to R, A or B or C or D are equally critical. With respect to theta, theta is minimum at A and D. So with respect to theta, either A or D is critical. Now overall critical point will be the point which are common in both cases. Means where overall critical point will be those points where overall critical points will be those points where R is maximum and theta is maximum, and both R is maximum and theta is minimum at A or D, because at A or D R is also maximum and theta is also minimum. So here overall critical point will be either point A and or point D. So you can take any point out of A and D as critical point to design. So suppose I am referring point A as critical point for design. So first we will calculate primary shear stress at point A, secondary shear stress at point A, resultant shear stress at point A. That will be maximum shear stress, because it is the resultant shear stress of critical point A. So first I am taking critical A as critical point. So first I am calculating primary shear stress at point A. Primary shear stress means stress which is coming due to force P. That stress will be primary, and due to force in welded joint always shear will come. So primary shear stress. And formula to calculate primary shear stress as primary shear stress in each point will be same, and that will be primary shear stress of point A also. And formula is total force P divided by total throat area. Okay. Here you can see total force P is 10,000 Newton and total throat area we are calculating in this page is 200 T. So total force P is 10,000 Newton and total throat area is 200 T. So magnitude of primary shear stress is coming 10,000 divided by 200. It is coming 50 upon T. Okay. Similarly, we will calculate secondary shear stress at point A or torsional shear stress at point A, which is coming due to moment P into E. Secondary shear. Now secondary shear stress at point A I am denoting as tau A double dash, and formula to calculate this is torsion moment T, which is nothing but moment P into E divided by J into R dash. R dash is distance of point A, because we are calculating for point A from CW, that is RA. Now torsional moment T is P into E, and value of P is 10,000 and A is 250 mm. You can check. So it will be 10,000 into 250. divide by polar moment of inertia. Now polar moment of inertia of this weld we have calculated, it is coming 1291666.667 into T. So it is 1291666.667 into T into distance RA, and distance RA we have calculated, it is 90.139. So from this equation we will get the expression of secondary shear stress at point A, and it is coming 10,000 into 250 divided by 1291666.667 T into 90.139. You can check calculation. Is it coming 174.462 divided by T. Okay, you can check calculation. So it is the primary shear stress, and it is the secondary shear stress at point A. Again I am checking calculation to be on safer side. Yes. So now we can calculate resultant shear stress at point A. So for that, first we draw primary shear stress and secondary shear stress at point A. It is So it is the direction of primary shear stress tau A dash. It is the direction of secondary shear stress tau A dash. We have already drawn, and vector angle between them is theta A. Now tau A dash value is this, tau A double dash value is this, and vector angle theta A is 56.31. So now you can calculate resultant shear stress at point A. Now the formula to calculate resultant shear stress at point A, that is tau A is root over tau A dash square plus tau A double dash square plus 2 tau A dash double dash cos theta A. And we already know the value of tau A double dash in terms of T and theta A. If you will put this, you will get the resultant shear stress at point A, and since it is the resultant shear stress of critical point, it will be overall maximum shear stress. And after calculation it is coming, you can check calculation, 50 square plus 174.462 square plus 2 into 50 into 174.462 into cos theta, that is 56.31 degree, then square root. It is coming 206.432 divided by T megapascal. Okay. Now overall maximum shear stress at critical point must be less than equal to permissible shear stress of the weld material. Now overall maximum shear stress is 206.432 divided by 2 T, and it must be less than equal to 100, because permissible shear stress is given in the question and it is 100 megapascal. So we will get the value of limiting value of throat, and it is coming 2.064 mm. It is actual throat, either it should be equal to this or greater than this. So limiting value of throat is 2.046 mm. Okay. Now we have calculated throat, so we can calculate leg. Leg will be throat is h by root 2, so h will be T into root 2. So 2.064 into root 2. After calculation, leg is coming 2.92 mm. You can check calculation, it is your part. So leg of this weld is 2.92 mm. Okay. So size or leg of this weld is, limiting value is 2.92 mm. Okay. If examiner is asking up to 1 decimal place, so you can put 2.9 mm. So size of this weld is 2.9 mm. Okay. Now we'll discuss another case of eccentric load in welded joint. So student, now we'll discuss type 2 of eccentric loaded welded joint. It is the type 2. Here you can see, suppose this is plate 1, this is plate 2, and they are connected like this. Okay, and we have joined this two plate by weld joint, and here this force P is acting. Now you can see, if you will transfer this point P, load P, but before transferring I am naming the axis. Suppose this axis as Z, this axis is Y, and this axis is X. In this diagram it will look like point. So this is X. This is centroidal Y axis. This is centroidal X axis for the weld, and this is centroidal Z axis. Okay, if you will make side view, this is centroidal X axis, it is centroidal X axis, it is centroidal y-axis and it is centroidal z-axis. Means, can I say the axis which are along the plane of weld, those axes are centroidal x-axis and centroidal y-axis, and the axis which is perpendicular to the plane of weld, that axis is centroidal z-axis. In this diagram also you can imagine plane of weld is like this. So centroidal x-axis and centroidal y-axis are along the plane of weld, and this centroidal z-axis is perpendicular to the plane of weld. Now suppose this distance is E. Okay, so if you will transfer this load P at the centroid, so for that we need to see, because in this diagram this is centroidal x-axis, so in this line centroid will come. Okay, so to see the perpendicular distance of this load P from combined centroid of weld, we need to see perpendicular distance of load P from centroidal x-axis of weld, which is P in this case. And if we will transfer this load P in the centroid, ultimately it will look like this. One force, direct force P will come in downward direction, and one moment P into VE will come in, act in clockwise direction. Now here you can see this force P is acting in downward direction, and due to force P, always primary shear stress will come, whether they are parallel to weld length or perpendicular to weld length, it will not matter during eccentric loading. And formula to calculate that primary shear is total force divided by total throat area, and it will be same at each point of the throat of weld. Now, but this moment P into E is important, because we need to see this moment P into E is welding moment for weld or torsion moment for weld. For that we need to see this moment is about along axis of the weld, plane of weld, or this moment is about perpendicular axis about plane of weld. Right now along axis for the plane of weld are centroidal x-axis and y-axis, and perpendicular axis for plane of weld is centroidal z-axis. Right now you can see this moment is acting about centroidal x-axis. In side view this is centroidal x-axis, you can see, which is the axis which is coming along the plane of weld. And since this moment is along the plane of this moment is about the axis which is along the plane of weld, means this moment will be bending moment for this weld. And since it is bending moment, due to this bending stress, that is normal stress will come. Means here due to force P, primary shear stress will come, and due to moment P into E, bending stress, that is normal, that is secondary normal stress will come. And since means nature of both is different, because due to force P, shear stress is coming, and due to moment normal stress is coming. So nature is different here. Okay, so to calculate stress here, you need to make the side view of this weld first. So this is side view. Right now weld is like this, it is weld 1, it is weld 2. Okay, and in this case you need to locate only the centroidal x-axis of this weld, because here this moment is like bending moment, and you already know, you have studied in strength of material subject. Formula to calculate bending stress due to bending moment is m upon I into y, where I is moment of inertia about neutral axis, and neutral axis is, if moment is about x-axis, neutral axis will be centroidal x-axis. If moment is about y-axis, neutral axis will be centroidal y-axis. Okay, so here this moment is coming about x-axis, so here centroidal x-axis will be neutral axis. So here we need to only locate neutral axis, and neutral axis will be centroidal x-axis. And right now this diagram is symmetric about x-axis, so in this diagram this centroidal x-axis will be neutral axis, so it is neutral axis of this weld, and it is nothing but centroidal x-axis. Now if you transfer this force P here, one direct force P is coming in downward direction, and one moment is coming which is about centroidal x-axis. Here it is like this, but if you draw the side view of this, it will look like this, because it is about centroidal x-axis. But don't focus much on sense here, only it is important this moment is coming in about centroidal x-axis. So I either draw in this diagram, draw about centroidal x-axis, either this or this, it will not matter a lot. Okay, it is the side view of this diagram. So this force P is in downward direction, and this moment is acting about centroidal x-axis, which is along axis of this plane of weld, and due to this moment bending stress will come. Now how to calculate stresses due to P and stresses due to moment P into E. So first I am explaining the effect of direct force P that I have already discussed. First I am explaining the effect of force P. Now due to force P, definitely primary shear stress will induce in the weld. Yes sir. So primary shear stress will induce. Suppose I am denoting primary shear stress as tau dash. Now to formula to calculate primary shear stress is total force P divided by total throat area. Okay, like for this diagram, suppose length of weld 1 is L, length of weld 2 is also L, throat of each weld is T. So total throat area of, for this diagram can be different for other case, but for this case total throat area will be, throat area of weld 1 is LT, throat area of weld 2 is also LT. So total throat area will be 2FT. So this is the formula to calculate primary shear stress, which is coming due to force P. Now, due to moment P into E, here moment P into E is acting like bending moment. So here moment P into E will be bending moment, and due to bending moment, bending stress will come, and nature of bending stress is normal. You can also refer this stress as secondary normal stress because it is coming moment. And why normal? Because it is normal stress. Okay, so I am denoting this bending stress as sigma B. Okay, now formula to calculate sigma B is bending moment, which is M, which is P into E, divided by I into Y, where I is area moment of inertia of weld about neutral axis. I is area moment of inertia about of the weld about neutral axis. And how to calculate I, that you have already studied in engineering mechanics and strength of material. But for this case, I am calculating value of I. How we will calculate? To calculate I, first we will refer this weld as rectangular weld. So what we will do? First we will calculate area moment of inertia. Suppose I am calculating I is area moment of inertia about neutral axis. Now to calculate I, first I am calculating I for weld 1 about neutral axis. Then I will calculate I for weld 2 for neutral axis. Then we will add both of them, we will get total I. So to calculate I for weld 1 about neutral axis, first we will calculate I of weld 1 about centroidal x-axis of weld 1. Now in this diagram, if you look at centroidal x-axis of weld 1, it will be middle of weld 1, and right now middle of weld 1 is this, because as neutral axis or centroidal x-axis of whole weld is also coming in this line. But this line is centroidal x-axis of weld 1, suppose C1A1. So first we will calculate area moment of inertia of weld 1 about its centroidal axis, means centroidal axis of weld 1, and the formula to calculate that will be BHQ by 12. B will be the dimension which is parallel to C1A1, and H will be the dimension which is perpendicular to C1A1. The dimension which is parallel to C1A1 is thickness of this weld, which is T, and the dimension which is perpendicular to C1A1 is length of this weld, that is L. So area moment of inertia of weld 1, area moment of inertia about weld 1 about centroidal axis of weld 1, that is C1A1, will be BHQ by 12. That is, here B is T and H is L, so TLQ by 12. But it is about C1A1. Now to calculate area moment of inertia of weld 1 about neutral axis, we will apply Parakram's theorem. For that, what will you will add area of weld 1, which is LT, into y dash square, where y dash is perpendicular distance between C1A1 and neutral axis. But right now you can see C1A1 is coinciding with neutral axis. So right now can I say perpendicular distance between these two lines is 0 and its square. So it is coming exactly equal to TLQ by 12. With same concept, if you will calculate area moment of inertia of weld 2 about neutral axis, it will the expression will be same as this, because right now weld 1 and weld 2 are symmetric. Okay, and if you will add both of them, you will calculate you will get the value of total area moment of inertia about neutral axis, which is I in this formula. Okay, so in numerical you can calculate this. So it is the formula to calculate bending moment stress due to bending moment M upon I. M is bending moment, I is this. Now what is Y? Y is perpendicular distance from neutral axis. Neutral axis is horizontal, so we need to take vertical distance. Okay, so through this you can calculate bending stress. Right now nature of both stress is different. So here we need to apply, we need to design this, we need to calculate principal stresses. After calculating principal stresses, we will use suitable theory of failure and we will design the material. Okay, but for that, first we need to find the stresses at critical point. It is the method to calculate shear stress, primary shear stress. It is the method to calculate bending stress. But we will calculate primary shear stress and bending stress for the critical point. And after calculating this, we will calculate principal stress and we will apply suitable theory of failure. So how to identify critical point in this case? It is very easy. In this case, nature of both stresses are different. First thing. Now the primary stress value will be same at each point. So can I say in this case critical point will be decided by the value of bending stress. Why? Because it is same every year. And the point at which bending stress is maximum will be critical point. And bending stress will be maximum at the point where Y is maximum. So to find the bend stress condition at critical point, can I say in this case critical point will be the point where primary and stress and bending stress is maximum. Primary stress is same at everywhere, and bending stress will be maximum at the point where Y is maximum. So can I say here critical point is the point where Y is maximum? Okay. Now To design, we need to find and where y will be maximum. For that, see the value of y for top point and value of 0.5 for bottom point, and maximum value out of these two value will be value of y max. Right now with symmetricities, you can see for top point value of y is, here you need to see vertical distance, value of y will be L by 2. For bottom point value of y is L by 2. So here maximum value of y is L by 2 if diagram is this. Okay, so y max will be L by 2. Now for design, first calculate primary shear stress at critical point, but primary shear stress at each point will be same. So that will be same as so that primary stress will also come same for critical point also. And the formula to calculate this primary shear stress, P divided by area of throat. So it is primary shear stress at critical point because it will be same at each point. Now calculate secondary normal stress, that is bending stress at critical point. And can I say at critical point bending stress will be maximum? It is not overall maximum normal stress because along with this shear stress is also coming. It is maximum normal stress due to bending moment, or it is maximum bending stress. Okay, for calculate overall maximum normal stress, we need to calculate principal stress because along with this shear stress is also coming. So it is maximum bending stress. And at critical point bending stress will be maximum because at critical point y is maximum. So formula to calculate this will be m upon I. M or I is same. Okay, and to calculate bending stress at the critical point, we will take maximum value of y, that is y maximum. So if you calculate y max, you can easily calculate this. Now this is normal and this is shear. So for design, we need to calculate principal stresses or maximum shear stresses. For that, first draw this diagram. And how to draw this diagram? In this diagram, this is bending stress. So draw, suppose this is the section in which stress is coming. So in this, draw bending stress. Bending stress is normal stress, so it will be perpendicular to this plane. And I am drawing this perpendicular bending stress as tensile nature. So it is bending stress at critical point. Now shear stress will be along the plane. So draw a line which is along the plane. Take arrow as your will. We want to take upward, down to take downward, take downward. It will not change the value of principal stress. So I am taking this in upward direction here, so it will be downward here. Now along with shear, complementary shear will also come. So shear is trying to rotate this lamina in anti-clockwise. So complementary shear will try to rotate in clockwise, and this shear is tau dash. Now you can see this is 2D stress condition, and 2D stress condition, it is the value of sigma xx. Whatever value this is coming, consider it as sigma xx. Consider this value as tau xy, and can I say here sigma yy is 0? So ultimately you will come to know value of sigma xx, sigma yy and tau xy for critical point where sigma yy will come 0. Now to calculate principal stress, first calculate radius of Mohr circle. This thing we have already studied. Okay, and formula to calculate radius of Mohr circle, that is capital R, is sigma xx minus sigma yy divided by 2 whole square plus tau xy whole square. You can calculate this. Here sigma xx is sigma bm, sigma yy is 0, tau xy is tau dash. After putting value, you will get the value of capital R. Okay, and after that you can calculate principal stress sigma 1, 2, and under 2D stress condition, formula to calculate principal stress is sigma xx sigma plus sigma y divided by 2 plus minus R. If you will take plus sign, you will get value of sigma 1. If you will take minus sign, you will get the value of sigma 2. And since it is subjected to 2D stress condition, sigma 3 will be 0. Okay, here sigma yy is 0, that is different thing. Okay. Okay, so sigma, we will ultimately get the value of sigma 1, sigma 2 and 2D stress condition, therefore sigma 3 will be 0. After applying suitable theory of failure, you can design the material. Okay, suppose examiner is asking to design the material by using Rankine theory of failure. In that case, you need to calculate overall maximum normal stress. Yes sir. Or overall maximum normal stress will be maximum value out of sigma 1, sigma 2 and sigma 3. Sigma 3 is 0. And with observation, you can say definitely here maximum overall maximum normal stress value will be equal to sigma 1. Whenever out of sigma xx and sigma yy under 2D stress condition, one term is 0, like here sigma yy is 0. And if sigma xx is of tensile nature, in that case definitely overall maximum normal stress will be equal to sigma 1. If you want, you can directly remember this. Okay, but if you will calculate sigma 1, sigma 2 through this relation also, you can see if you will take plus sign, you will get sigma 1, and sigma 1 in sigma 1 sigma xx by 2 and r will get add with each other. If you take minus sign, they will get subtract with each other. So so definitely since sigma xx by 2 and r is adding in sigma 1, so it will come more than sigma 2. So definitely in this case overall maximum value will be sigma 1. You need not to remember this. Through this relation you can conclude this. Okay, but here suppose examiner is asking to design by using Tresca theory of failure. So for that you need to calculate overall maximum shear stress, and actual method to calculate overall maximum shear stress is mod sigma 1 minus sigma 2 divided by 2, mod sigma 2 minus 3 by 2, mod sigma 1 minus sigma 3 divided by 2. And maximum value out of this 3 value will be overall maximum shear stress. But in 2D stress condition, if you want to remember, if out of sigma xx and sigma yy one term is 0, like here sigma is 0, in that case overall maximum shear stress will always be equal to capital R. This I have explained many times. If out of sigma xx and sigma yy one term is 0, then overall tau max will be equal to capital R. If you want, you can remember that. But it will not always be equal to capital R. When under 2D stress condition, out of sigma xx and sigma yy one term is 0, in that case overall tau max will be equal to capital R. Okay. But suppose if examiner is asking to design by von Mises theory of error, then you need to calculate both sigma 1 and sigma 2. Sigma 3 will be 0. So by applying suitable theory of error, you can design this material. If suppose in question permissible normal stress is given, permissible normal stress means directly overall maximum normal stress should be less than equal to sigma p, because directly permissible normal stress is given. So then to calculate overall maximum normal stress and ensure that is less than equal to sigma p. If in question directly permissible shear stress is given, that is tau p, means you need to only calculate overall tau max, and that overall tau max must be less than equal to tau p. And if material in question tensile strength is given, then definitely examiner will mention which theory of failure to be used, and after that they apply that theory of failure and design the material. Okay. Step is calculate tau dash, calculate maximum bending stress, then draw this and calculate principal stresses. If you want to calculate overall maximum normal stress, that will be equal to sigma 1. If you want to calculate overall maximum shear stress, whenever in 2D stress condition out of sigma x and sigma y one term is 0, in that case if you want, you can remember overall tau max will be equal to capital R, that is radius of Mohr circle. So it is the eccentric load type 2 of welded joint. Okay. I am solving one question related to this. It is a question. A cantilever beam of rectangular cross section is welded to a support by means of 2 fillet weld as shown in figure. A vertical load of 2 kN act at the free end. Suppose I am denoting this load as, I have drawn this diagram separately, P, which is 2 kN in Newton, it will be 2000 Newton. Now this distance is 40, this is 50. Considering that allowable shear stress of weld material is 60 Newton per mm square, means permissible shear stress is directly given, it is 60 Newton per mm square, means overall maximum shear stress either it should be equal to 60 or less than 60, means here to design we need to calculate overall maximum shear stress of critical point. Now the minimum size or leg of the weld required will be, so examiner asking about leg of the weld. Now for that first transfer this load P at this location. Again suppose this is Z axis, this is Y axis, so this will be X axis. In front view it will look like point, this is X axis, and we'll draw the side view of this weld. It is already drawn here, but I am drawing here a bigger diagram. Suppose this left side weld is weld 1, it is weld 1. This right side weld is weld 2, it is weld 1, it is weld 2. Length of both weld are 40 mm. You can see this length is 40. Here all dimension are in mm. I am not mentioning. So it is 40 and this distance is 50. You can check the diagram. Okay. Now here you can see, if you will transfer this point P, load P at centroid. So here it is centroid, in this line centroid will also come, and it is centroidal x-axis. So here one direct force P will come in downward direction, which is 2000, and to transfer this load P here we need to find its perpendicular distance from this, and that perpendicular distance of load P from this line is this, which is equal to 150 mm. I am denoting this distance as E, which is eccentricity. So if you transfer this load P at this location, one moment will come, that is P into E, which is about centroidal x-axis. Now see, centroidal x-axis is the along axis of plane of weld, or it is perpendicular axis of plane of weld. So you can see plane of weld is like this, and this is centroidal x-axis. In side view also you can see. So centroidal x-axis is the along axis of plane of weld, and since this moment is coming about along axis of plane of weld, means it will act as bending moment for the weld. Okay. So here in this diagram, first locate centroidal x-axis, because moment is coming about centroidal x-axis. Since this diagram is symmetric about x-axis, so centroidal x-axis will be exactly in the middle. So it is the centroidal x-axis, and it will be neutral axis for bending moment. Now here one direct force P is coming in downward direction, and this moment P into E is coming about acting about centroidal x-axis. So in this view it will look like this. So it is moment P into E, and since it is about along axis or about of the weld, that's why it will act as bending moment for this weld. Now what we will do, first we will calculate due to force P, primary shear stress will come. Yes sir. And due to moment P into E, and primary shear will be same at each point, and due to moment P into E, I am denoting this moment is A, this moment is bending moment, so definitely due to this bending stress will come. Now we first will calculate this primary shear and bending stress for critical point, and that point will be critical whose distance, perpendicular distance from neutral axis, that is Y, is maximum. Okay, we have already located neutral axis. Now if we calculate distance of top point from neutral axis, it will be half of 40, that is 20. If we calculate distance of bottom point from neutral axis, it will be half of 40, that is 20. And maximum value out of value distance of point or distance of top point from neutral axis and distance of bottom point from neutral axis will be Y max. And right now both distance is same, which is 20 mm. So can I say in this case value of Y max will be 20 mm. Okay, so you can take either top or bottom point as critical point, and at that critical point value of Y is 20 mm, which is Y max. Okay, now we will calculate primary shear and bending stress for critical point. But to calculate primary shear, first we need to calculate area of throat of the weld. So suppose throat throat thickness of this weld is T. So area of throat of weld will be, throat area of weld 1 will be length is 40, so 40 T. Throat area of weld 2 will be 40, length is 40 and throat is T, so it will also be 40 T. So total throat area of weld is 80 T mm square. Now we will calculate area moment of inertia of this entire weld about neutral axis. For that, first we will calculate area moment of inertia of weld 1 about neutral axis. And how we will calculate? First we will calculate area moment of inertia of weld 1 about centroidal axis of weld 1, that is about C1A1, which will come exactly midway of this, and neutral axis is also coming in the midway, so it will coincide with neutral axis. Now area moment of inertia of weld 1 about C1A1 will be BHQ by 12. B is dimension which is parallel to C1A1, in this case it is throat. H is dimension which is perpendicular to C1A1, in this case it is length of weld 1, which is 40 mm, so into 40 cube divided by 12. Now to calculate area moment of inertia of weld 1 about neutral axis, we will apply Parakram. Parakram will be area of weld 1 into Y dash square, where Y dash is distance between C1A1 and neutral axis. But right now C1A1 and neutral axis is coinciding, so Y dash will be 0. So this is area moment of inertia of weld 1 about neutral axis. With symmetricity, area moment of inertia of weld 2 about neutral axis will also come same. Now total area moment of inertia about neutral axis is I, and it will be I1 plus I2. And if you will add I1 and I2, it will come 40 cube divided by 12. It is coming 5333.333 divided by T, sorry, into T mm to the power 4. Okay, so now we'll calculate primary shear stress and bending stress at critical point. So primary shear stress is the stress which is coming due to force P, and primary shear stress I am denoting as tau dash. It will be same at each point, means it will also come same at critical point. Its formula is force divided by total throat area. Force P is 2000 Newton and total throat area is 80 T. So primary shear stress at critical point is coming 2000 divided by 80. It is coming 25 upon T. You can check calculation. Now we will calculate secondary normal stress or bending stress at critical point. Bending stress will come due to moment P into E, and bending stress at critical point will be maximum, which I am denoting as sigma Bm. It is maximum bending stress, and formula to calculate this is M upon I into Y max. M is bending moment. Right now its value is P into E. P is 2000 Newton and E is 150 mm. You can check. Divided by I is area moment of inertia about neutral axis, which we have calculated. It is coming 5333.333 T. You can check calculation. 5333.333 T into Y max. For this question, value of Y max is 20 mm. So maximum bending stress is coming 2000 into 150 divided by 5333.333 into 20. Check the calculation. Is it coming 1125 divided by T? sorry, here I had done one mistake. This, if you will calculate I1 plus I2, it is coming 10,666.667 T. You can check calculation. I1 is this, I2 is also this. If you add both of them, means we need to calculate twice of this. It will come this. It was slight calculation error. So value of I is not 5333.33 T. It is 10,666.667 T. So if we calculate maximum bending stress at critical point, it is coming 2000 into 150 divided by 10,666.667 into 20. It is coming 562.5 upon T. So it is maximum bending stress at critical point. So now we'll draw the stress condition at critical point. Here bending stress is coming, whose value is sigma Bm, whose value is 562.5 upon T. Along with this primary shear stress is coming, it will be along the plane. Now to this shear, complementary shear will also come. This primary shear stress nowadays, its value is 25 upon T. Now it is sigma xx, it is tau xy, and here sigma yy is 0. And since permissible shear stress is given, we need to calculate overall maximum shear stress. Now it is 2D stress condition, and in 2D stress condition, if out of sigma xx and sigma yy one term is 0, here you can see out of sigma xx sigma yy one term is 0. In that case, overall maximum shear stress will always be equal to radius of Mohr circle. But it is not same for all cases. It will be, overall tau max will not be equal to R for all cases of 2D stress condition. Overall tau max will be equal to R for 2D stress condition when out of sigma xx and sigma y is one term is 0. In that case, it is 100% sure overall tau max will be equal to R. Now formula to calculate R is square root of sigma xx minus sigma yy divided by 2 whole square plus tau xy whole square. Right now sigma xy value is 0. Now if you put the value of sigma xx, it is sigma xx, and value of tau xy, you will get the expression of overall tau max in terms of T, and it is coming 562.5 divided by 2 whole square plus 25 square. You can check calculation. Is it coming 282.359 divided by T? It is the expression of overall maximum shear stress. Okay. Now this overall maximum shear stress must be less than equal to permissible shear stress of the weld material. Overall maximum shear stress is 282.359 divided by 2, and it must be less than equal to permissible shear stress, which is 60. So we will get the limiting value of throat, and it is coming divided by 60. Throat is coming 4.706 mm. It is limiting value of throat, means actual throat either it should be equal to this or more than this, because to be on more safer side, actual stress should be less, and actual stress will be less when throat is more, because it is coming below side. So whatever limiting value is coming, actual throat either it should be equal to this or more than this. Now our objective is to calculate leg of the weld. Now throat is h by root 2, so h will be t into root 2. So if we will calculate leg of the weld, it will come 4.706 into root 2. After solving, it is coming 6.655 mm. You can check calculation. 6.655 mm. So it is the leg of weld, and actual leg either it should be equal to this or more than this. Means you can also say it is the minimum required value of leg, because actual leg should be equal to this or more than this. So limiting value of leg is 6.655 mm. Examiner asking round off to 1 decimal place. So if you will round off to 1 decimal place, it will be 6.6 mm. So it is the limiting value of lower leg for this question. Okay. Now we'll discuss some special case in welded joint, that is circumferential weld. Only you need to remember the formula of area of throat, area of moment of inertia about centroidal axis, and polar moment of inertia of circumferential weld. Rest of the analysis is same, which we have discussed for all other type of weld. Okay, and here this analysis of circumferential weld will become easy, because you need to directly remember the formula of area of throat, polar moment of inertia, and area moment of inertia about centroidal axis. Like the formula of area of throat for circumferential weld is, first we'll consider circumferential weld first we'll draw the line diagram of this. And suppose the radius of this circumferential weld is r and diameter is d. Diameter will be twice of r. Now here this diameter is inner diameter of this weld, and you can also refer this as mean diameter and this as outer diameter, because whenever we are taking any distance, we are ignoring the thickness or throat of or thickness of the weld, because as compared to thickness, diameter or radius will be high. Okay, so you can say this, you can refer this diameter as inner diameter also, mean diameter also, and outer diameter also, because all these three value will be near to each other. Okay, and suppose throat thickness of this weld is T. So T is throat of the weld, and D is diameter of this weld, whether it is inner, outer or mean, it will be nearer to each other. Now to formula to calculate area of throat is pi dt or 2 pi rt. The formula to calculate area moment of inertia about centroidal x-axis, which is along axis for this weld, or centroidal y-axis. The formula to calculate area moment of inertia is pi t r cube, where t is throat will be equal to h by root 2, that is different thing, and r is radius of this weld, whether it is inner, outer or mean, because they are nearer to each other. The formula to calculate polar moment of inertia of weld, that is J, is add both of them and it will be 2 pi t r cube. You need to remember these three formulas. Like suppose it is a circumferential weld, right now it is subjected to torsion moment T, and here lag of the weld is h, diameter of this shaft or beam is d, and we have to find it is capital D. By mistake I have written small d, and we have to find the expression of maximum torsion shear stress. Now you can see this torsion moment T is nothing but it is this T moment T is torsion moment for this weld. Why this is torsion moment of this for why this is torsion moment for this weld is because this moment T is acting about this axis. This moment T is acting about this axis. This is a z axis. Suppose this is y axis and this is x axis. X axis and y axis is along axis for the plane of weld, and z axis is perpendicular axis for the plane of weld, and this moment is acting about z axis, that is axis which is perpendicular axis for the plane of weld. If you will see in this side view, this moment T is acting like this, means it is acting about centroidal z axis which is perpendicular axis for the plane of weld, means it will act as torsion moment for the plane of weld. Now due to this torsion moment, the torsion value of maximum torsion shear stress will be T upon J into R, maximum value of R. Now T is torsion moment. For this case, formula to calculate polar moment inertia is 2 pi T R cube, and R max will be, you can R max is maximum radial distance from centroid, but when we are finding the distance, we will refer this diagram as line diagram. So if you will calculate its maximum radial distance from centroid, it will be equal to R, and you can take R as inner radius also, mean radius also, outer radius also. Actually it should be R naught to calculate R max, but here while taking distance we are assuming thickness is very less. So while taking distance, Ri, R naught and R will be near to each other. So I am rightly writing distance R. So this formula will come T upon 2 pi T R square. But now examiner is asking this formula because in question diameter is given and lag is given. So we have to modify this formula in terms of lag and diameter. So T upon 2 pi, and T is lag, sorry, T is throat. Now throat is nothing but h by root 2. So we can replace this throat T by h by root 2. Root 2 will come top side. Now R is radius and R will be diameter of this by 2. Now if diameter of this shaft is D, so diameter of this fillet weld, circumferential fillet weld will also be D. It will be inner diameter, but right now inner, outer or main diameter all are nearer to each other. So radius will be D by 2. So here we can replace this R square, R by D by 2, and if you replace it will be D square by 4. D square by 4. 4 will come above side. Now 4 divided by 2 is 2. So this formula is coming 2 root 2 T upon pi H T square. So maximum torsion shear stress for this case is 2 root 2 T upon pi H D square. 2 root 2 T upon pi H D square. 2 root 2 T upon pi H D square. Which option is correct? Option C. Okay. Similar manner, I am also discussing one more question. In this case, this welded component is subjected to bending moment M. Now, and this weld will be circumferential weld. Why? It is circular in cross section. So definitely this weld will be circumferential weld. Okay. Now I am drawing this diagram. Okay. Now if we will make the side view of this circumferential weld, it will be like this. Its inner diameter is d, so inner radius will be r, which is d by 2, and this will be inner radius r. Okay. Now if you will see this movement is acting about is z axis, which is perpendicular axis for the plane of weld. This is y axis, and this is x axis, and x axis is along axis for the plane of weld. And you can see this moment is acting about x axis, and x axis is along, sorry, here z axis is perpendicular axis for the plane of weld, and x and y axis are the along axis for the plane of weld. And this moment is acting about x axis, which is along axis for the plane of weld. Means, can I say this moment will act as bending moment for the weld, because it is coming about x axis, centroidal x axis. If inside you will draw centroidal x axis, it will look like this, and this moment M is acting about centroidal x axis, so it will act as bending moment for this weld. Okay, and here this centroidal x axis will be nothing but neutral axis, and due to this moment M, bending stress will come, and we have to find the value of maximum bending stress. And the formula to calculate maximum bending stress due to bending moment is M upon I into y max. M is bending moment, and I, area moment of inertia about neutral axis. And area moment of inertia about neutral axis for circumferential weld, formula to calculate this area moment of inertia is pi t r cube. So formula to calculate I is pi t r cube, where t is throat and r is radius. And value of y max, y is perpendicular distance from neutral axis. Neutral axis horizontal, means perpendicular distance, we need to find vertical distance. And maximum value of y will either it will be at top point and at bottom point, and at top point or bottom point value of y is equal to r. So can I say in this case value of y max is equal to r? So if we simplify this, it will come m upon pi t r square. Now I am simplifying this relation in terms of leg and diameter. So t is throat. Now throat is nothing but h by root 2, where h is leg of the weld. So if we will replace m upon pi t by h by root 2, here h will come and root 2 will come above side. R is nothing but it is r is equal to d by 2. So if we replace r by d by 2, it will be d square by 4. So here d square will come and 4 will come above side. So after simplifying, expression of maximum bending stress is coming 4 root 2 m upon pi h d square. So it is the expression of maximum bending stress, 4 root 2 m upon pi h d square. Which option is correct? 4 root 2 m upon pi h d square. Which option is correct? Option C. So it is the analysis of circumferential weld. So we have completed the topic welded joint, in which we have discussed what is introduction of welded joint, then type of welded joint, then analysis of butt weld, then analysis of fillet weld, in which first we have understood terminologies of fillet weld. Then we have done the analysis of parallel fillet weld, in which we have discussed two cases: symmetrically loaded parallel fillet weld, then unsymmetrically loaded parallel fillet weld. Then we have discussed the analysis of transverse fillet weld. Then we have started one most important topic, that is eccentric loading in welded joint. In that case we have discussed two cases, type 1 and type 2. After that we have discussed circumferential weld separately. Okay, so now we have completed this entire chapter of welded joint. Okay, this is the complete team of mechanical engineering, that is team Drona of mechanical engineering. Is Devendra Negi sir, Apruv sir, Amit Dikshit sir, Vishwajit sir, Sandeep sir, Kuldeep sir, Vinay sir, Vishal sir, it's me, your RB sir, Ratan sir, Aditya sir, Vinod sir, and Swadesh sir. Okay, so thank you very much. See this whole lecture and try to solve or practice the problem as much as possible, as much as you can. Okay, so all the best for your preparation, and in next lecture we will meet with some another topic of machine design in this one short series. Okay.